So, what do you understand by the word X-ray? Uh-huh. You say what? Talk now. Are you not confident? Talk. So right, X-rays. No, the type right. X-rays are radiations that form part of the electromagnetic spectrum. That forms part of the electromagnetic spectrum. Are we there?
Yes.
They form a part of the electromagnetic spectrum and have high frequencies. Are we there? They are the second most energetic radiations. They are the second most energetic radiation after gamma ray.
Okay.
Are we together? They have their usefulness and importance in both crystallography and public health services.
Usefulness in crystallography
And public health services. And public health services, if you don't, you can see, and medicine. Are we together?
Yes, sir.
Okay. So please, what's the typical wavelength of X-ray?
10 raised to power minus 8 to 10 raised to power minus 12.
Please write it down. That's it. The X-ray ranges. The X-ray ranges. They range from 10 raised to power of minus 8 to 10 raised to power of minus 11 meters. Are we there now?
Yes, sir.
How about their frequencies? Their frequency range from what? 10 raised to power of 16 to 10 raised to power of 18 hertz. Photon energy. They have a very high photon energy of about 100 kilo electron volts. In fact, that one too ranges. It can produce from 100 electron volts to 100 kilo electron volts. That's the photon energy they can produce. But when it comes to their speed, they travel with the speed of light. They travel with speed of light, which is 3.0 times 10 to the power of 9, raised to the power of 8 meters per second. Are you together there? Who discovered X-ray? Who discovered X-ray? A man named Wilhelm Röntgen. He was the one that performed the experiment that formed the first common X-ray. And what kind of them? He used the same setup as the cathode ray tube setup. So let's go. Right. Wilhelm Röntgen was the first to discover X-ray. Wilhelm Röntgen was the first to discover X-ray and named it so.
This is past.
What is it?
I named it so due to the past.
Due to the fact that the ray now characteristics of X-ray. Characteristics of X-ray.
Okay. No.
Number one, it has no electric charge. Yes, no electric charge. Does not have any electric charge, and yet it has no mass. See that? No electric charge. We have no electric charge. Number two,
They have no mass.
they have
No mass.
no
Yes.
mass. Another thing about them is that they travel in straight lines.
Travel in a straight line.
Are you there?
Yes.
They cannot be deflected by an electric or magnetic field.
Right. They can't be deflected.
They can't be deflected by a magnetic or electrical field. Are you there?
Yes, sir.
They cause ionization of gases. They cause ionization of gases.
They cause ionization of gas.
Then they penetrate many materials. They are very, very much penetrable. They have a high penetration and they can produce fluorescence. Are you there?
Yes, sir.
Are you done with that?
Yes, sir. No electric charge, no mass. Traveling in a straight line. It can be affected by magnetic or electrical field because ionization is gassy, high electrical fragment, produce chloroquine.
Yeah. So, production of X-ray. So, production of X-ray. Production of X-ray. Now, I know I've told you guys about this before. Where is it produced in the first place? Inside the cathode ray, right? You utilize the cathode ray, also known as the discharge tube. So you need a filament inside the cathode ray that heats up, right? And then it can start heating up to just start taking part in thermic emission, the generation and release of. That's what's going to happen again. So let's go. Number one, it is produced in a cathode ray tube. It's produced in a cathode ray, in a cathode ray tube.
Yes.
Good. Now, what are the things that you see in the cathode ray tube? See something like this.
We have the filaments, the tungsten, the vacuum pump.
Tungsten is usually the anode.
Vacuum pump connected to the potential difference.
Are you sure? So, what's the working principle of this guy? Very, very simple. It depends on the one you want to produce, Abby. So, I'm demonstrating for, let me write it here, classification of X-ray. Okay, I'm already, since I've drawn this. Although they will do both the running X-ray and the other one, they will do this. You have to pass through this. So that I can still do it with X-ray. We have
typical X-ray and characteristics of electron.
typical characteristics.
Electron. And the correct way to pronounce this is shallow X-ray, right?
Yes. Huh. They always too loud for morning. Don't you have peace in this cell of you? Be peaceful. You know, you become in peace like early morning. What are the working people? So we're starting with atypical. Was you respond okay?
Sure that we
First thing first we want to talk about is that we will heat up the filament. The filament is heated from this end.
that
Yes, filament gets heated. And as we heat up the filament, what do you expect to happen? Thermionic emission, which will cause the release of what? Electron. So there will be this is followed by thermionic
emission the release of electrons.
release of electrons. Also,
That from what?
you just give this one. Did not tell you that I'm not in a good mood. That's what it is. What is it?
This is followed by thermionic emission, the release of electrons from a high
Maybe it's a quality. It's correct. Sure, the correct. If I hear a voice of that, the both of you will get project you will not finish today. You will see. Make I just hear voice for example my ear. The high food, then now that we have produced this thing, the next thing is that we want to generate massive acceleration. So a high
A high peak is established. After a high peak is established, next statement.
They don't consider these things. You don't just drop down. That's anything.
So,
Can you what is this? Oh yeah, now let me start dictating for where I stopped. You think I was lying when I said you do project today? Just watch. Thank God, I don't have people who know to tell the other ones coming. You think you go today, both of you? You go, let me bend. Walk through for you. Yeah. So, X-rays. You saw my, like, you just go to church on Sunday, but you're not in the choir. You just talk to church, you started to talk. Yeah. So, what did I write about X-ray? X-ray. What's your notes? What's your notes too? That is the mic. That's okay. I didn't know that. Talk. This one. Okay.
there are radiations that form part of the electromagnetic spectrum. Share to mind what you said. Okay. So there are radiations.
Was that right there somewhere? But this one, since it's rubbish, you want to say.
So the whole part of the electromagnetic radiation, they have high frequency, short wavelengths. Their frequency ranges from 10 raised to power 16 to 10 raised to power 18 hertz. They have wavelengths, they have short wavelengths ranging from 10 raised to power minus 8 meters, 10 raised to power minus 9 meters. And
what's that 9 meters? You see what I'm saying?
minus 9 meters now. It's not.
So, you can drop. Once I'm done with this class, I want to see your listen, both of you. You submit this banded project on X-ray. You present it today by 6 o'clock. So, let me just be doing the explanation for you. So, X-ray, they are very, very, very useful radiation. They have their use both in what they call the medical field, or in agriculture, they have it everywhere. Just that. So I already used it to a good extent. I was discussing the what they call the production. So that's how I'll start from. So the production of X-ray starts like this. It's practical. There is a discharge tube. Now, at the cathodic region of the discharge tube, that's when they have a heating filament. The heat of the filament, and the filament start producing what? Electrons. Via what process? Thermionic emission. So in your paper, if they ask you about this and you want to present it, you can use the micro because you see. So if they ask you a question about it and you want to present it, you have to make sure you're saying it chronologically. The first thing that happens is what? Heating of the filament. After the heating of the filament, what happens next?
Acceleration of the electrons.
Acceleration. Good. Now, when the accelerations Now those electrons are accelerating. Where are we accelerating them towards?
What's tungsten?
So we wanted to move towards the tungsten, right? Which is their targeted material. And when they get to tungsten, what do they do next?
Okay.
How?
By hitting the
Meeting. So when we target those elements, right? We've targeted them, they've struck them with X-rays a lot. Then we will now do what? Then we will now fire the X-ray continuously so that some of them will go and strike in between the cells of the individual and go straight into the what? Where is it going to go to?
decay shell.
And to go out into the S and K shell. In the S shell and K shell. I get it now. That's where you go to. Now, what? Now,
Okay.
now when the X-rays get to that target, you are now moving macroscopic. I get it now. At that point in time, funds are not available much. But by the time you go there, come back, print, money has finished. So once the radiations enter into subatomic level, right? What you observe is what you see that the X-rays have lost their subscription for the payments is gone. What I mean by their subscription, I'm talking about they probably would have stopped classes, yes, and then they will not hear they're taking the modules, virtual parts. Why some will come late? I show you that we have already becoming late since you're not here. Today that you came early, you don't let us hear what. Now you now is young player, yeah, but you still do the project, but yeah. The restaurant of them. After all this things have happened and they struck the target now, then you will now go on to finish up the work because you can't submit AI slide like that with AI in front. Now, rubbish. Like, it's something you can do on time, you can do everything. Do it again, and I just do everything. You read your slide, yes. That's what you just do. I'm serious with you. So, but nevertheless, this one, once the radiation passes through the atoms of the space of the tungsten, right, they will meet things that look like this. So look at it. Look at it. The electron can come and deflect this one. This one will now get deflected away and form waiting. It will form a void in this place. That void is formed. Is it a good void? Is it a bad void? No. Until you made yourself something and it will represent.
Okay.
So,
Okay, so you get Designated heat dissipation comes to void.
Can you?
Yeah, then can you?
Alright. So once the electrons are approaching this place, they knock off electrons in inner shells. Sometimes it can be from here they knock off, sometimes it can knock off from the innermost shell. Remember the name KLMNO. But once they knock off, they form a void. I get what I'm saying now. They form what?
A void.
A void. This void formed. Electron from the higher orbital will now have to jump and cover that void. But the moment they form this void, the radiations that comes out from the formation of the void, that radiation that comes out as a result of kinetic energy is X radiation. You can see now, it's called what? X radiation. Very simple. Very, very simple. Very, very simple. So yeah, X radiation.
So this is typical of reference.
I told you that this is for typical X. Yes. Your other X ray, that one do not do collision with anybody. I get what I'm saying now. What those ones do is this. Once they are getting close to, yes, they approach this region. They know that you will create as a force. You know, these things have a negative charge.
Yes.
So when they drop the phone on the floor, the children pick it and bends. So that force that tends to cause this thing to appear like it's in the bed, that force there is what leads to formation of a brain stratum X-ray. That's it. That's it.
I said because we didn't speak from that side. I said attraction, like in this accelerated electrons and the move close because yes,
That's part of your this because it is you and your teammates. That's why I'm not repeating anything I've mentioned in that class. So you better go and start as soon as you are free. But before then, let us deal with Joan Hunt's law, which is used in determining what? Minimum wavelength. And you are producing minimum wavelength, doesn't mean you are producing minimum energy. No. In fact, the idea is maximum energy. Thank you very much. Thank you very much. So yes.
Okay. Someone is six.
What is it?
The drawers.
Okay, the Joan Hunt's is not a law. This person is an educator. And wife, husband rather,
Right there.
and wife to, and not, yes, she's a lady now. No, very for you. And wife to a high person in her community. So basically, you get to find out that X-rays were not fast. There's some of them that looked inert as if they don't move nor react. Some of them are react. So that's why you see them bring it out in different categories. You see some, they don't put inside food, buy some, they still put more on. This? Yes. CC. HC over C. You get why? You get why? Don't worry.
E was against you, and then now we
That denominator become your energy. I know. We are living like this. Now, this place that is here, are you getting me now? Represent compartments. Yes. Compartment of where the vicinity of that electron is, because that's where the energy generation is going to start from. That's why we did it like that. So, even if you want to do it, leave it that other way, you can put it there energy. Or we will put it there as C. So people can remove it and put MU. That's momentum. Depending. So you have this. You have this. This is the rough calculation I'm doing. But this E, like I said, it's representing a kind of energy, a compact energy that measures what vicinity you removed the particle from. For example, it's electron removed, right? So this is the electron measured in electron volts. If it were to be that I created a space within the sphere of the orbital cloud, we usually used to use C. That's why it's what I use like that. So if you want, for your level, since I already use, if it's explained to you, just leave it as EV, as energy in electron volt. I've taught you how to convert from electron volt to joules.
I'm calling it for minus 20.
How do you convert from electron volt to joules? What do you do to the number? Do you divide by 1.6?
Multiply by
Good.
1.6.
Good. So from here now, you are able to come to a conclusion that what? Okay, I'm written like this. But if you want to calculate the energy of the site from which you created the stuff, what will you do? You will cross multiply. Utilizing to if you would have been equal to H. Do not break anybody's wall. Do not go and dig somebody's floor. In the name of you are looking for something scientific. The catch you is your own. No. You are strictly on your own. Number next, the question. Given that JC is equal to 1240 HC. Given that HC is equal to 1240. Are we together here now?
Yes, sir.
If I put that HC here as 1240, I get it now. What will be my vote if lambda is 60? If lambda is 0.0207? What will be the value of EV?
Equals to 4.59 times 10 raised to power 4.
I didn't hear you.
Is it? That's 4.5.
I didn't hear you. Okay. EV together, abi? Is it the EV together? You did this by this?
Yes.
Eh? Okay. So it gives you 4 points. Is it EV or election vote that is? You keep that one. So your characteristics X-ray. Your characteristics X-ray. How do they appear?
They appear when they hit the tungsten, and inside the tungsten, they hit an electron in the inner shell, and then which causes a void. And then when a void is caused, and the orbitals, the higher orbitals, tend to fill it up until there's continuous filling up of the void, and then it uses that as explanation.
Okay. Okay. So,
Okay, next.
all right. Characteristic X-rays appear as sharp peaks. They appear as sharp peaks.
Sharp peaks.
Characteristic X-rays, right? They appear as sharp peak superimposed images. They appear as sharp peak superimposed images on the continuous spectrum. Now, the photon energy itself, the photon energy is given by E equals to, the photon energy is given by E equals to E upper, energy at the upper region minus energy at the lower region.
Okay.
Now, Moseli's law. Written Moseli's law. This was postulated by Henry Moseley.
This was written by Henry Moseley.
The characteristics, the frequency of characteristic X-ray depends on the atomic number Z. Then write the equation. What's the equation? What's the equation? What's the equation for the characterization by mostly? F from where? The square root of V. Square root of V equals to A open bracket Z minus B. I did it in chemistry. I just use F for any function of V. Yes. Then what is that Z that is there? B income. The screening effect. I know that's not the ordinary atomic. It's not about atomic, it's the effective nuclear charge. It's nuclear charge. Not just the atomic number, just then X-ray absorption. And X-ray passes through matter. As X-ray passes through matter, yes, then their intensity decreases.
Okay.
As X-ray passes through matter, their intensity decreases. Write the equation for that statement. I is equals to I naught in raised power minus mu x. I'm writing the equation. Mu x minus mu x, where mu is the linear attenuation coefficient. Linear attenuation coefficient. What did I tell you the meaning of attenuation in the last class? What did I tell you the meaning of attenuation? Attenuation. What happened to them? No, like, aside from, why is it that you even, if was that's really ever looking for food? What was the ever looking for in the time? Don't worry. Thickness, just right. X stands for thickness. Read the formula. X stands for thickness of absorber. Who is the absorber? What's the name of the material? Metal. Tungsten or molybdenum. Right, where I naught, you've written the equation, Abi. Where I naught is the what? Initial intensity. I is the transmitted intensity, of which you know that when it's transmitting, it will be annihilation pair. Annihilation pair are the effect that tends to bring down the camera quality of something without removing the base correction for contour. X is thickness of absorber. Okay. Half value layer, HVL.
So I said half.
Half value layer, HVL.
Half value layer.
Mm-hmm. What's the half value layer? It's just like half-life. It is the thickness of the material required to reduce the X-ray intensity to half its original value.
Like the thickness.
It is the thickness of the material required to reduce
Required to reduce
the X-ray intensity
the
to half its original value.
to have its initial value.
So how do you denote it? How do you denote it to talk fast?
I don't know how it's denoted.
Since it's half-life now. So I'm giving you the general expression through attenuation equation. Since it's half-life, no, that is not half-life, it's this one that is in terms of gradients. So you're not saying with company. Okay, you don't do anything of such. I know why. So I do what? I not.
I know the initial.
I not the initial intensity now. In the previous formula that you wrote, is it not I naught over 2 equals to I naught E is power minus mu x? What do you write?
Equals to I naught E from mu x.
That one is for X-ray absorption.
Yeah.
I'm asking you about half value layer. Okay. Even in that your X-ray absorption, anyway, you see I ordinary I, put I not divided by 2. What does it mean? You're trying to say that that's like you want to, I don't know if you get, half the price. That means what will be left after the initial I not is going to be half of the total. Are you there? What did you get? What's the new equation?
I equals to I naught over E power minus mu x.
Okay.
Okay.
Next thing is diffraction grating. Diffraction grating.
So what's diffraction rating?
Okay, do you remember when we did X-ray, how we were calculating using that N2 to find 2 distance?
Okay, under Braxton.
Yeah, that's diffraction. That's Bragg's diffraction grating. with, like, when we did that diffraction breathing, did you solve question that day? We solved that question plenty. Okay. So that's right. X-rays have wavelength comparable to atomic spacing. Wavelengths comparable to atomic spacing. Yes. Making them suitable for studying crystal structures. Making them suitable for studying criminal structures. Or studying crystal structures.
Okay.
So write the formula, the Bragg's law equation.
N lambda equals 2 beta lambda.
I've written it. Let me see. I said you should write it. You know what? So N stands for what? N that stands for what? N? N stands for diffraction order. Then we have lambda for wavelength. D stands for spacing between crystal plane, and theta stands for the Bragg's angle.
So N lambda stands for.
What is it?
N lambda stands for.
I don't get you. Try lambda. Is that an Igbo name? I'm hearing N lambda.
N lambda.
Okay. N. They are not together now. They are separate things. N is an integral. Lambda. You can. They are on normal speed. That one is when you are trying to. You can use that to check if a wave, two waves are constructive or destructive interference. It's not as if all of them now call them one name. You use it to determine if a wave is constructive or destructive. What do you mean by path difference? What did we see Bragg's law state? He said that if a wave is constructive, then the wavelength must have a whole number of a wavelength, Abi. The whole number of wavelengths is that not n lambda separate things? N is the whole number of a wavelength. If n is not a whole number, it means it's destructive. Oh yeah. Medical application.
It's our application.
It's used in diagnostic radiography.
Using.
Diagnostic radiography.
Okay. Using diagnostic radiography.
Yes. Used in CT scan. CT scan. What's the meaning of CT? What do you call it? Siditarian. What is Siditarian? It means computed tomography. Computed tomography. CO. MP. TO. MP. PM.
COMP.
This guy want to repeat it. COMPUTED. Computed. Tomography.
Using.
This is the mammography, fluoroscopy, image guided surgery. Diagnostic radiography, computed tomography, dental imaging. Everything is not first. There are still many more things the medical applications for. Fluoroscopy.
So those are for medical application.
Number next, engineering application.
Engineering application.
Number one, non-destructive testing. Number one, non-destructive testing for welds and casting.
Okay, number two. Number two.
Cargo, no, inspection of aircraft components.
Number 3.
Detection of internal cracks.
Okay. Inspection of internal cracks.
Then quality control in manufacturing.
Quality control.
What is that? Microelectronic inspections. Microelectronic inspections. Then they also apply it in biological effects. There's a difference between medical and biological. DNA. DNA is a biological effect. DNA is a biological effect.
So what are
They use them to check for potential effects in DNA damage, test for potential defects in DNA damage, in increased cancer risk with excessive exposure, increased cancer risk with excessive exposure.
Okay.
Skin burns at high doses.
Skin burns at high doses. Okay.
Cataract. Very good. Cataract. Cataract is part of the thing they use to diagnose. Reduced fertility is not causing it, it's used to diagnose it, to notice everything you are seeing here. They not say it is causing it to not only diagnose. All of them, some of them here, they can help you to diagnose it, some of them they can help to treat it. You get, but it's not the majority here for damage. For cataract, it can help you notice cataract and soft X-ray. But every other one is it can burn. Increase risk for excessive and yes. Reduces fertility at high doses. Anti-doses. Um, um, but let's answer. I was going to take a break. And again, I'm having. We are done with the biology. Precautions which you should follow to reduce the effects, exposure to those effects. Number one, you have to minimize exposure time. Then maximize distance from the source. The source. Oops. That's enough. No. I was doing just no, I'm not leaving completely.
I'm standing. I'm standing. Let's see something else.
Hey, that's me.
Then maximize distance from source.
Then using appropriate shielding. Because of this, it's picking what you are saying. And limitations. Yes, no. The rest. I was still not in this one. It's considered I'm doing it. True many materials.
Number 3.
Fast image acquisition.
Sir?
Fast image acquisition. Valuable in medicine, engineering, and research. I'm telling you, stop that stuff. You don't understand. I'm not sleeping for about 6 days. I'm having delirium, confusion. It's triggering it. That's why I'm reading from this slide. That's what I'm saying. Stop. Valuable in medicine, engineering, and research. And then limitations. Ionizing radiations poses health risk. Ionizing radiation poses health risk. Then an X-ray tube. An X-ray tube operates at 80 kilovolts.
That's a question.
Yeah. No, yes. An X-ray tube operates at 80 kilovolts.
Okay, let's take a look.
My point will stay on me, don't worry. My point is still on me. You talk to go. Tell me. Determine the minimum wavelengths produced. Determine the minimum wavelength produced.
So here we have sorry, knowledge of density over compactness energy.
Sorry, I can't.
I said knowledge of density over compactness energy. I'm really giving both as step two.
Okay. What do you need?
You need compactness energy.
They didn't give you the. They've given you KB direct. They've given you KB already direct. Is it not HC over EVA already also? Or which one?
6.67 times 10 raised to minus 30.
I'll check.
What's the answer?
Or which one? Which one? The one I told you guys, right? 0.0155. 0.0155. Did you get it?
So what did you use for your energy?
What formula did you use?
I I use HC over compactness energy. For my compactness energy, I need 30 kilovolts times 1.6 times 10 raised to the power minus 19.
Well, now they not give us how many parameters did they not give? Mm. Mm. Going to use
Minus left.
hello. You are going to use minimum wavelength equals to a constant 1240 divided by V, where V is your voltage. That 1240 has integrated H, C, and E inside. Bye bye.
That is 1,200.
1240. Can you ask me something? After you did it, what's the answer? Bring your calculator. I can see you pressing 1,240 divided by 3, 30,000. Did I say divided by 30,000? The vote in your question is how many?
An extra tube operates at 30 kilovolts, determine the minimum wavelength.
It's 80 kilovolts, I said. Yes.
Zero point 0.0155.
Yes. It's not, that's not what. Times 10 is power of what? It's nanometer like that.
So mine is not nanometers, so 0.0155. That's 0.0155.
I've heard you.
0.0155.
You are correct. I've heard you. I said it before. Just now. I said no, that you're wrong. Sorry.
Okay, next question.
Just remain 30. Eh?
Next question.
Small.
No. Bernoulli's expansion. Now you have your P1 plus, what again do you have? Rho what? Over 2 rho V squared. Normally you're supposed to have a plus Z, which some people will write it as what? Rho G Z. Some people write it rho G Z. But normally it is just Z. You have the one here, you have the one here. You say it's equal to P1, P2 plus 1 2 rho V22 plus Z2. The reason why I'm mentioning these three pressure rates is because they have high tendency of coming out this year. Based on information, so you don't even want to, you don't want to be in that situation where something as simple as that will be giving you issue. Take note of that. Now, there are two concepts in that question. What are the two concepts? Aside from Bernoulli, what's the second one? Continuity. What does the continuity expression say? A1 V1 is equal to what? A2 V2. Do we get that? Now, most times, did they give you the area in this one? Downtown. How many of you went to go and look for your area? There was no need to do that, no time. This expression still works as the 1 square V1 equals to the 2 square V2. There's no point because when you open that area, you're still going to cancel that pi over 4. It is going to be left D. This of it that is going to convert to radius. You're still going to cancel the pi in that radius. The whole function of dividing the dam is something that will cancel out. So this still works very fine. Now the question there is, mention two apparatus, two equipment that Bernoulli is used as a testing theory. Because you ask you, which of the following is a Bernoulli tube? Which of the following is not a Bernoulli tube? Mention any two Bernoulli tube. Mention any one. You should be able to mention those things. So what are the two tubes that makes up the Bernoulli tube where you can apply Bernoulli? You have the venturimeter, and you also have the what? The orificimeter. These two things are utilized in your Bernoulli. Why? Because they both have a constriction at their what? At their throat. They call it throat or their neck. You will see it like this, and this is the constriction here. You see that? That is what we refer to as a venturimeter. So you have the venturimeter, you also have the what? The orificimeter. Those two things, very useful when it comes to what? When it comes to Bernoulli, precisely hydrodynamics. Now, another thing, everything I'm telling you are things that I'm confident you will need them to actually pass this exam. No jokes. Now, how many kind of viscosity do we have? And that's not even the problem. Being able to name it just helps you escape that kind of situation, OBG. The real issue is, can you differentiate between the functionality of the two of them? What are the two kind of viscosities? Thank you. You have the kinematic viscosity. The kinematic viscosity. And you have the what? Dynamic viscosity. Which one of these viscosity describes the real internal fraction between layers of a fluid? And which one of them is dependent on the other? Dynamic viscosity is for which one? What makes sense? For the what? Thank you. The other one is not fake. It is the independent viscosity. This one depends on this one, right? That's why you will see that you say the kinematic viscosity is equal to the dynamic viscosity all over what? Density. Which one there is controlling, is responsible for the difficulty in transferability of fluid from one container into another container? Which one of them? It is kinematic. Dynamic is the resistance to it being stirred. Are you getting it now? That's why they call it kinematic. It is the kinematic. You can't easily transfer. But this one resists force, dynamic. Steering is actually a forceful kind of thing now. Do you understand now? So please have that at the back of your mind. Okay. I just have to touch you there first in that dynamics. So what's the moral lesson from dynamics just now? Moral lesson? Go and read it. I think I already told you that. Sorry, thank you, Papa. I'm coming. Can I use myself? Exam, because it's going to come out 100%. It's going to come out. You can't escape the whole of viscosity. It's not going to happen. So just prepare for it ahead. So, okay, I'm here. So, the things you've learned from that now is you must know how to operate calculations on the VR tube and the OR tube. You must know the difference between the two types of viscosity. Are we together here now? Good. Hydraulic press application. Hydraulic press application works on the principle of what? Yes, on the principle of pressure, but what is that thing about pressure? OBJ question. Does pressure increase as you at altitude increase? It increases with depth, Abby? Good. Now, there is this question that you might likely see under this arrangement of different density of fluid. So this is, it will tell you, this place contains fluid A, sun is fluid B, fluid C, right? Now, they will now want to ask you, this place here, normally they can just do something like this and make you understand that this is the head fluid. We know that what? That which of them experiences the highest pressure? Good. If you want to write the pressure expression of this arrangement, of this stratification, how will you write it? No, I just said the arrangement, the mathematical expression that I was going to use to write it. No. Pressure and fluidity can never be equal to this one. So how are you going to write this expression? Thank you very much. The correct expression is atmospheric pressure plus the real V of this one. That is real C V G plus what? Real B V B G plus what? Real A V A G. This is how to do it. If you go and start from this one, you are wrong. You must start from atmospheric because that's the one that will be acting at the surface here. That's how to arrange it. This gives you the pressure in this stratified column. Please, there isn't too much. There isn't overwhelming amount of things to learn. But the few you want to learn and enter, learn it with confidence. Learn it and be confident. What are the 5 forces? What are the 5 forces that act on a fluid? What are the 5 forces that act on a fluid? Can you? Pressure force, gravitational force, thank you very much. Buoyant force, no. Viscous force, that is the same one under buoyant, whether you call it viscous or buoyant. Thank you. Force of compressibility. Force of turbulence. Under what condition of these 5 forces is Bernoulli's equation derived? Under what condition of these forces is Bernoulli's equation derived? Under which of them is Navier-Stokes derived? Okay. Good. So when turbulence and compressibility is equal to 0, you have gotten Navier-Stokes. Do you get that now? Very, very simple. Very, very simple. But when turbulence, listen to where you got it wrong. Pay attention. When turbulence, compressibility, what's the one you mentioned that you see? You mentioned only gravitational for Bernoulli. Abi? For Bernoulli. Bernoulli's turbulence and compressibility is not just one. Turbulence, compressibility alongside with this buoyance. That is where you form Eulerian fluid, Eulerian force. Do you get it now? So please, you better note it down because I'll ask you these questions. I'll ask you those questions. Ask you those questions. Now, when you have a buoyant force, before I even ask you this question, let me be sure that you understand. What's the difference between hello? What's going on at the back? What's the difference between buoyant force and upthrust? Mm-hmm. And the obtuse is the coefficient of buoyant force. The force is buoyant force. That's why it has force with it. Obtuse is like the parameter within the buoyant force. Just the same way coefficient of friction is inside frictional force. Do you get the concept? Okay. Everybody, write this question down. An object for those of you that are math students, it's only that maths. At this point in time, you should have known how to project projectile on an inclined plane. You've done it already. Projectile, you should have been done with all these things. Now, right, an object is projected. An object is projected at an angle 30 degrees to the horizontal. At an angle 30 degrees to the horizontal. Are you there? What is its component of velocity? What is its component of velocity? What is its component of velocity at the exact point of impact with the projection plane? At the exact point of impact on its projection plane, given that initial velocity was 100 meters per second. So we are looking at something like this. That we want to know what velocity did they use and strike the floor. There is a lot to learn. Let's see what's going on. Okay, how did you go about it? Tell me, discuss it. Everybody pay attention, please. Huh? Okay.
Because we have to find its component of velocity at the exact point of the impact on its projection plane.
Okay. So how did you get the Vy? How did you get the Vx at that point? Any? Okay. 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 No matter why. As the final point, that's because that's land. Pay attention. In any projectile you do, we've discussed this thing already during this thing. Just as some of you, the session you applied for was not what you felt, so it's you. Now, you just decided to use today to revise everything you get. Now, very good step you started with. Look at, I'm talking to you. You're looking for what the Lord lost. You started well to have resolved. And that one, now you knew the velocity was what? What velocity did you take up? 100 meters per second. That means Horizontal component will be what? 60. That's what value now? Maybe you used it. What's the value in present? 86.6. This one here is 50, I mean. 50. Now, the question there is this now. So, we are looking for what? Oh, Jesus. What's now, the moment this object is moving here, there's only one thing you need to remember in life as a student that are very projected. You see this horizontal component of velocity? In every projectile, it does not change. So even if they tell you, calculate the projectile of the body when it was caught on the air at so point, the horizontal component does not change all through the journey. In this place, even at maximum height, it does not change. That's why at maximum height, velocity is not zero. Anybody that told you that has lied to you. The only time velocity is zero at maximum height is vertical projectile, where it does not have horizontal components. In this place here, maximum height, we still have horizontal component. That's the one that made him swing. But he couldn't go up again because vertical component here is equal to zero. So therefore, the resultant velocity at maximum height is equal to the what? Horizontal component of what? Velocity. Because that's the only one existing here. Now, when you get to this final place, the final velocity of horizontal component is still equal to what? Ux, which is the initial, because it does not change all through the journey. Is this point what? It does not change all through the journey. Why does it not change? They can ask you, explain why this one, they will draw the diagram, explain why horizontal component of velocity at this point is equal to the initial. The reason is because the definition of projectile says that what? Any object thrown into space that is a projectile is a body that only moves under the action of what? Gravity. Only is the most important thing in that definition. Leave grammar. If you, so some of you like to write a projectile is a body that moves in a parabolic path. That one you're even writing nonsense first. Now then, maybe your own nonsense is a bit matured. A projectile is a body thrown into space and allowed to move under the influence of gravity. You are still writing nonsense. But if you do not, your definition is not showing that gravity is the only source of acceleration, you are writing rubbish. And if it is true that gravity is the only source of acceleration, it means in every projectile motion, it is only vertical components of velocity that will be changing because there's something accelerating it. So that means horizontal never changes. Nothing to accelerate the body again. Now, we want to look at what will now happen here. Abi, a very, very simple task. All I need to know is the time it takes to move from here to here. Once we know that time, we can now find what the velocity here is. That is vertical component of velocity here is. How do we do that? Watch. I will come here, I will say, watch one. What's the time of flight? The time for you to start from there to get to the end. What's the time of flight? T is equal to, that one is normal now. 2U by G. That's the time of flight. T will now be equal to what? 2 times 30 sine what? Over 10. Sine 30, that's this one will be everything up here. These two cancel this one, Abi. So we're left with 3 seconds. True of course. So it took 3 seconds for the object to move from here to here to here. Do you get me? Why that one? Sketch it. That is 30. Okay. Sorry. 100. I thought it's 30. It's 100. So that means the answer is what now? 10. Takes 10 seconds. Now, that we know that it is 10 seconds they used to get here. The question we'll now ask ourselves is this. Look at you will now write out the vertical component of the motion happening here. Bring it outside. Look at it. Remember this formula. V square equals to U square plus or minus 2G. I'll use minus GH. There's still another one that we have. V is equal to what? U plus what? Or minus GT. I will use this formula. Why? Because I have to. Now, this whole formula now, the way we're going to use it is that we're going to be using only vertical component. Only what? So this final velocity, I would call it vertical final velocity. This one, initial vertical component. And when I started the motion, it was going up, Abi. So minus G now waiting 10. T now waiting 10. Do you know we have the value of UI? UI is this one, 50. So put it there. Vy may now be equal to what? 50 minus what? 100. Vy is now equal to what? Hello, hope you know that if you do not get minus, you're supposed to know that the answer is rubbish. Why is it going to get minus? That minus tells you that what? That the object has crossed to the descending side during that time interval. You don't get? I pity you. I'm not in the mood to repeat anything today. I will repeat this one. I said that when you finish getting this, like this kind of question now that I did, you still have minus here. If you don't get minus, as a student, you're supposed to know that you have done rubbish. Because before I even started, I'm expecting to get minus. Why? I know that within that time, 10 interval, because that 10, I calculated it as time of full flight. So I know that at that 10 interval, this object is supposed to be in the descending side of the motion. It's supposed, because initially when it was here, this is how its two-dimension will be. It's vertical will be pointing up. But when it gets here, I'm expecting it to now be like this and how? Down. At this place, it's going to be like this and impact down. Now, we've been able to get the final velocity. That means final velocity is 50. It strikes the floor with 50 meters per second vertical components. And what's the horizontal in that place? 86. So therefore, what's the velocity between to use and strike the ground? 86.6 square plus what? 50 square. Whatever answer you get, meters per second, 90. Sometimes they will tell you at what that you should obtain the angle of impact. When you struck this floor here, obtain the angle of what? Impact. How do you get the angle of impact when you struck the floor? Theta will be equals what? Tan inverse of what? Which one is y component? 50. All over what? Good. What's the answer? A question like this has high tendency of coming out this year. High tendency. What's the answer? 30 degree, Abi. If you write 30 degree, you are wrong. You are not getting your full mark on that. I promise you, 100%. And this is not WAEC now that they used to pity people. No. Because obviously, this is the resultant line. They are trying to tell the examiner that you're supposed to have sense. 60K. It's here that is 30. How do you mark your line? Like this? Like this. How do we count? From here, 90, 180, 270, then the remaining here is 60, Abi. So 270 plus 60. That is 3. Is it 350? No, it's not 350, 330. So either you do 360 minus this 30, or you understand? It gives the same thing. 330 degree. If you don't want to be writing all this, I'm doing all those plus and minus. This thing here means east 30 degrees south. You must be, it's not direction you're getting. You must state it in bearing. Make sure you don't use ordinary G here. You use G cos alpha, where alpha is the inclined plane lift. There's no time to start deriving it. But that's the same thing that happened with, it's the same thing that happened with time of flight. It's still the same thing that happened with maximum height. Range is the only one that is different. Oh. Let's go. Now, another important thing you need to watch out for in this exam that you're going to go and write, you need to watch out carefully for is where these people are coming as students in AC circuit. They are coming at you with some kind of, if you are here, you don't know the meaning. I'm sure that those of you that participated have been following up with the GWR lectures. By now, you should have known the meaning of, because they will tell you, so they know you know the meaning of impedance, right? You know impedance, right? Admittance of an AC circuit, susceptance of an AC circuit, reactance of an AC circuit, power fraction of an AC circuit, how to identify if a parameter is a, because this word I help you. Okay, I supposed to believe it. Sorry. Is a lag or a lead. By how much is it lagging or leading? As simple as this thing may be, it will come out, students will not be able to write anything. And they are very simple. What's the meaning of impedance? Impedance is simply the what? Resultant of all the reactants. Who are the reactants? XL, thank you, ancestors. As well as what? Resonance. Condition for resonance. Impedance is simply the what? The resultant of your XL and your XC, as well as your what? Resistance. This is resistive reactance. We have your capacitive reactance, you have your inductive reactance. Then admittance is the opposite of impedance. Impedance means impede. Just like saying resist. That's why all of them are ohms. All these people are measured in what? Ohms. They are all resistance kind of parameters. That's why they call them reactants. And the summation of all of them is an impedance. We are impeding you from all angles. Either you are coming in as a capacitor who can use time and generate some stored charge, or you are coming in as a, we will catch you, no worry. That's the impedance one. Then the opposite of impedance, which is saying the reciprocal of impedance, is admittance. If they tell you define admittance, admittance is the reciprocal of impedance. It is denoted as Y. So it's just for you to carry all your reactants, invert them, you'll be getting, you see they use X for impedance parameters, they use Y for admittance. So we still have YL and YC. Oh, no. Susceptance is for inverse of each of the reactants. The inverse of each reactance. Now, don't get twisted. Inverse of impedance is admittance. Inverse of each reactance is susceptance. The power fraction is obtained when? How do you obtain your power fraction? By obtaining your what? The ratio of your CT. This is the power factor, and it's usually equal to what? It's usually equal to XL, which is greater minus X divided by what? Divided by R. You know it, you are safe. AC circuit is the full 10 marks for you if you come out. But if you don't know it, jam in your mind just what your job is doing. You don't be doing that. Now, power fraction, it defines, that's what tells you how to present your answer in AC circuit. See, 90% of students that understand AC circuit, when they are writing their final answer, it's rubbish they are writing. And it's there to tell you to catch people. They know that the steps might not be the problem for you. To clamp steps, they hard. It's to present the final answer. The student can finish solving. I want to present his answer of maybe the power factor. You're not going to write this one is equal to do my power factor is equal to, because somebody told you the formula, you have scrambled the formula. You just do xm minus xc over r tan inverse and put answer there. You are failed with that one, you don't get any mark. Because the way you're supposed to present it is state it in your answer. Is XL greater than XC? If yes, my power factor lags by the tan inverse of whatever you got here. That's how to write the answer. My power factor lags by this. Why is it a lagging this thing? It's a lagging stuff because XL is greater than what? C. The only time we have a lead is when XC is greater than XL. And the only time we have a resonance is when XL is equals to XC. No this and no peace. When XL. And this is usually the case most of the time. This is usually the case most of the time. You know why? See something. You don't want to write out this one in full. You just have to write it. Which are the lines? Angular velocity L, which is the same thing as what? 2 pi f L. Did I do 1 all over? But if you want to do xc, you are doing like that will make the value small. So in a case where upon this kind of inversing, that the xc is not greater than xl, that's a lead. That means the capacitor, the current flowing over the capacitor was leading by, usually by 90 degrees. Was leading by 90 degrees over the other one. So when you state it, you put your factor there, you don't have a problem. So that's it for that. Now, you see, all these kind of things, you can just put them in your mind, small, before you know it, you are good for your exam. You don't need to kill yourself. Now, inside the same resistance, you can ask you one very simple thing. What is the frequency? OBJ question, it has come out before. I'll tell you the way it came out. And I'll tell you the way I'm expecting it to come out again this year. If they bring that one out this year, I'm expecting it. Because you probably never repeat question word for word again. I'll tell you how they would likely want to do it. You are Nigerian. Nigeria is also supply the power supply. To ask you, what is the frequency of Nigerian power supply? Then you know there was a time in JAM, and when I read to ask about the votes, the home supply votes, where everybody is picked 240, 222, 240, 220, 240. Now, frequency. What's the frequency of Nigerian power supply? The frequency is what? Is 50 hertz. USA is the one that is 60. Now, how do they present it to you? They will tell you in OBJ. Which of the following is true of the frequency of light of alternating currents? Which of the following is true of the frequency of alternating currents supplied in Nigeria? Option A, 100 cycles per second. Option B, 50 cycles per second. Option D, 200 cycles. The correct answer will be what? Thank you very much. People will go and rush and pick 50 cycles per second because they had mentioned 50. They've forgotten that what I mentioned was 50 hertz. And if I want to translate hertz to cycle things, it is one full cycle is a to and fro complete. Frequency sits down to and fro as one. That's why it appears as 50. But the correct thing as well to pick is 100 alternations per second. So this light, the meaning of that statement is that this light, this alternating current, is actually coming up, going up, coming up, going up, coming up, coming up. 100 times in a second. Imagine, for that to happen 100 times in a second, your senses won't be able to pick that thing to know that it's actually happening. Lots of countries like USA where it's happening 120 times each second, the light will look static. And in this one, I even still notice that it's shaking one kind. I can still notice the vibration. That's how the case is. That's how the case is. You must know this. It's just the fact. That one is the show something. You can't dodge it. This is circuit. Can't dodge it. In your magnetism and magnetic field, under what condition do you use Fleming right hand rule? And under what condition do you use Fleming left hand rule? Under what condition do I use the right hand thumb rule? Under what condition do I use the left hand thumb rule? Okay, yes. What about the other one? Now, how about when I am studying, maybe I am utilizing Laplace force equation, the F equals to BVQ. What rule do we use there? What rule do we use? Right hand rule. But under what condition do we use right? Under what condition do we use left? When it is positive, when the Q is positive charge, you're supposed to use your right hand. Use the negative charge, you're supposed to use your left hand. But no, people don't know. Right hand for both. Right hand for both. You have to note that. All those things have to be noted. See that capacitor? Go and read your capacitor very well. Go and read your capacitor very, very well. Especially the derivations for the different type of capacitor. Let me just give people a clue. Go and name the one for uniform cylindrical capacitors. Yes. Uniform cylindrical. Let me go back to my question now. Let me see. Yeah. In thermodynamics, in your thermodynamics, what is CP? What is CV? And what parameter relates the two of them? Okay. That is specific is at constant. Okay. Now, if you are giving your CP and you're not giving your CV, how do you get your CV? No, CP minus. Keep it in your head. But they are looking at me as men. Also know that the ratio of those your molar specific heats can give you your what? Specific heat ratio Y. It's like gamma. Note it down, no. There's no time again. Oh yeah. Question available. Write this question down. There's no time. Do you know how to calculate your coefficient of performance? What is it? Coefficient of performance. Hello, nobody? Coefficient of performance. Even from this side, coefficient of performance. Uh-huh. I did. Very simple. People should not joke with your exam. Oh. Yeah. They all create salvation. Sharp, sharp. Now, if you guys are in the hall, better those of you here, better still be listening. You better be listening from me. If you guys are in the hall, and they tell you, briefly describe pair annihilation of S-ray and attenuation of S-ray. Explain formation of Bremsstrahlung S-ray and characteristic S-ray. What are you going to be saying? Pair annihilation. Mm-hmm. Okay, good. Now, what about attenuation? That one is the difference. That's trying to get through. Attenuation. It reduces with what? It reduces with thickness. The more it's passing through, it's intensity dropping. What equation did we use in demonstrating that? Okay. All right. Write this question now. Yes, pair annihilation. Attenuation. That pair annihilation, they've asked that thing before, last year. That's how you know that this year they're asking attenuation of X-ray. Yeah. It's not the same. It's not the same. Pair production is a process that happens sometimes before pair annihilation will occur. You want to create or produce a radiation or a particle that can substitute another particle in the subatomic level of the radiation. But it is not exactly the same process. It's just that it is a substitutionary process if they tend to cancel out. Sometimes their intent is to reproduce a new radiation. So they're not exactly the same. Look at this question. A newly discovered star has its maximum radiation at 240 nanometer. Determine the surface temperature. The total, that's surface temperature is A. B, total power radiated. Total power radiated per square meter if the star behaves as a black body. Yeah? Per square meter, yes. If the star behaves as a black body. This question has 70% showing up this year. Before I tell you that you're going to have 70%, it means some lecturers outside Lagos who are also taking part in this are already advising their own students and people they know. After all, go and focus on this part. Focus on this part. It's not left for students to see, they will not read it. Maximum radiation, yes. 240 nanometer. Those of you that are that side, let me tell you something. Both those that are there and those that are here, you better try your best to make sure you stream all the parts that you have missed during the lecture. So you know be found one thing. It should be there. I don't know. I might upload it. Once they upload it, just go on. 2.4. Okay, what is this one for? Yeah, I didn't what? Okay, yeah. Okay. Deborah, I saw when you came in. I saw when you came in. I saw when you came in. Came late. You came late. You nearly crawled to go and sit down. In your mind, I did not see you. You wanted to crawl, you wanted to crawl. Then when you sat down and thought I don't catch you, you're not comfortable. You now want to blend. Your fair face has been shining when you entered. What you say? I don't just want to feel somehow when I do H at the middle of your bench. That kind of thing when you're entry class, if you have a successful, now your H should stand. Now, that question that people are dying on, don't worry. It's a 2-second question. And it's 2 seconds. The question is a 2-second question. Go and check 2021 past question, it's even there. Anybody that once you start wasting time, it means you don't do it in your GPA program. That's because it's Rien's displacement. Minimum, sometimes they will use the word direct. They'll tell you, this one they use calculate the minimum displacement. Just a new discovered star has its maximum radiation. I mean, good. So once you are saying all those words for maximum radiation gives minimum wavelength. When they tell you something as the maximum radiation, what property of the radiation are they talking about? Is frequency. So if they say it has its maximum radiation cap at this, they are talking about the frequency of the radiation it produces. So we know that if something has a high frequency radiation, it means that that thing has high energy, and energy is inversely proportional to wavelength. Something that has high energy has the small wavelength. So if I tell you that this is a maximum frequency, that means that thing is the minimum wavelength. So that's what they use there, and is equals to temperature multiplied by the constant, Wien's constant. Finish. So remember, it's not wasting time. The person knows 2.989, the most easiest constant to remember. What is it? Even if you don't remember, you can just suppose cap it at 3, because the effect will not be far. Say you don't even remember, so you just cap it at 3, because the power 2 is raised to the power of 3. But just that is minus 3. It's power of minus 3. So we'll still use 2.898 instead of power of minus 3 without per Kelvin. That's the easiest equation in the whole of O4. Then the second part B. Hello, those of you that are there. Part B. We don't know the question we are doing. Your life. Because they put ribbon in front of your seat, you think you're in right table. It's your life. What? That second one, they said the total power radiated per square meter if the star behaves as a black body. That's once they say behaves as a black body, emissivity is equal to 1. That's the radiation. They went to radiation. This formula that you know already, radiation. Rate of let me just call it rate Q. Rate of heat transfer by radiation is equal to what? Emissivity, Boltzmann constant, area, T raised power 4. The relationship that you are needing in this one. This relationship you need for the question. Because they told you already about the Q over A. Now check. The main definition of the Q over A. That's the total power per square. Because Q is rate of heat flow with time, which is power. Well, so the formula left is E Boltzmann T. Oh, they're giving you this and they're giving this. They gave you this as a word when they said blackboard 1, right? And already when they mentioned this, you know that this thing is already a radiation of something. Kevin Boltzmann constant will come into play, which is also very easy to remember. No, not 23, minus 8 and 5,678. 5.67 times 10 to the power of minus 8. That minus 23 own is normal Boltzmann. Very good. The wavelength of maximum. So good. Very, very good. Very, very good. Very, very good. The constant, Wien's constant, W-E-I-N, Wien's constant, 2.898 times 10 to the power minus 3. Now, in that physical quantity and units, every single person go and learn Buckingham's method of dimensional analysis. I said it, and I've taught it. when you find a number of pi, because Buckingham, B-U-C-K, B-U-C-K-I-N-G-H-A-M. I don't know if the video is uploaded by next week. You can just check maybe at the beginning because that was part of the first. Now, that's that vector analysis, vectors, OBJ. In fact, before then, Jupiter asked you classify physical quantities. What are you supposed to write? What are the class of physical quantities? Classify physical quantities. What is what is it called? So, yes. Yes. If they ask you to classify physical quantity, you let them understand that physical quantity can be classified based on 5 categories. Category 1, by mathematical nature of the quantity, where you have rank 0 tensor, came out last 2 years. When they ask them, which of the following is a rank 0 tensor? When they say rank 0 tensor, what do they mean? Scalar quantities. The number in front represents the directions to which they act. So, based on their mathematical nature, we have rank 0, rank 1, and rank 2. Rank 0 are scalars, rank 1 are vectors. Are you following what I'm saying? Then, who are the rank 2s? Those ones, they create action. Their action creates effect along multiple planes. If I create a force here now on this bottle, the boss is going to feel the force only in that direction. But a rank 2 tensor, when it creates an action in one direction, it stimulates effects in many directions. That is plane. It will have effects in many planes. Know that and know peace. What is the condition for it's coming out from let me know what's in on life. What is the condition for orthogonality? Condition for vector orthogonality. People don't know the exact orthogonal rights. Maybe I'm thinking it's one thing like that. Yeah, maybe they're using last step. Somebody's they're showing last step past question. There's one there. Yes. Forgetting that his last step is started new syllabus. Not paper type syllabus. See, some people show syllabus. You've seen that they started the last 2 years. They don't start the year they release it. People are part of the fresh hands. What happened? Like you are blessed. The first sons. Hello. What is the condition for orthogonality of a vector? Orthogonality. What's the condition for collinearity of a vector? You don't know these 2 things. You want to go and write the exam. Don't worry. Let me tell you, you're supposed to be sleeping with reading table on the express. On the express with reading table. Not use go torchlight on that sun reading. I pity you. Because some of these things are not hard. You are not just studying. Orthogonality now means condition for a vector to be perpendicular. How will you feel to now come out and find out that's the meaning what they are saying? Collinearity is condition for the vector to be parallel. And it's very easy to know. Scalar vectors and your vector product. It's a scalar vector. Scalar product and your vector product. In your scalar product, inside your scalar product, what do you think has to be there to make your vector occur at 90 degrees to one another? What do you think has to be in place? Okay, this is what I will ask you. What condition makes you have a maximum vector product? Is it when theta is 0 or when theta is 90? Remember that vector product ends with sine theta. When theta is what? That's when you get maximum, abi? Very good. Maximum. So if they're asking you what is the condition for orthogonality, you are telling them that it is when the vector product is perpendicular to themselves, or when vector product is maximum. They can ask you, under what condition is vector product maximum, OBJ? You will see when they are orthogonal, when they are perpendicular, which is orthogonal. Collinear, where do you find it? Parallel. Because that's the same thing you see when you are doing all this Laplace force equation. Because you see that we're working with angle from the vector, from the field rather, to the what? To the normal. So when the magnetic field is now lying on the normal, that's when it's perpendicular to the what? Surface, and gives you maximum flux. So you can see that now proves that the product of your magnetic fields are what quantities? Are vector quantities. Because they depend on the rules of vector quantities. Don't go and confuse things though. It was what I talked about now was what? Magnetic flux. If you like, go and write that your magnetic flux is scalar and write magnetic field is vector. You know they are not the same. Magnetic flux density, magnetic field are not the same thing. Chineke guys is the one that will help you. Okay. Eh? Your circular and oscillatory motion. Don't play. Elasticity. Don't play with it. Too. Hope you know your conditions for energy in a spiral spring, in a series arrangement of a spring and parallel arrangement of spring. Good. Then you know how to solve complex spring system. Spring systems. Go and learn it. Okay. Your length maker equation. How many of you have mastered it? The length maker equation. Combination of thin lenses. Your combination of thin lenses. How many of you understand, can explain the types of aberration of a lens like this now? As I said, you can explain the aberrations. The lens aberrations. They've done, but we've done it. You've not revised it. I remember Mr. Ben took it. Mr. Ben took it. Oh. Don't worry, that means maybe you feel that those things are nonsense. You don't even know what it is. Yes. When you did spherical aberrations, common aberrations, Abi, go and learn your aberrations well. I've told you. Go and learn your aberrations well. OBJ. Eh, what property of photoelectric effects? I remember man mentioning this. What property of photoelectric effects affect the number of electrons that will be ejected? And which one will determine the energy with which the electrons will leave? The what? Frequency. Exactly. Do you know the? Do you have your ear in the second part? Do you have your ear in the second part? Intensity contributes to what if photoelectric effect? Number of electrons ejected. Frequency contributes to what? Energy with which the electrons will leave. That means they determine the kinetic energy of the electrons. In your circular and oscillatory motion, in that circular and oscillatory, let me tell you something. There's some of you that are in this place. By the time you see that question that will come out there, you might just leave it. And you know that you only not pick any two questions out of one, out of two. It's now pick one out of one. Because you toyed with that topic in the wrong way. You are here at this point of your life. You cannot derive equations under circular and oscillatory motion. You all know. You don't know how to derive maximum acceleration. This is well. One truth is, you have to read. That's all it. That's all it. Write this question down. See this question. So, a symmetric double convex lens. A symmetric double convex lens has equal radii of curvature. Has double convex, has equal radii of curvature. R1 is equal to plus 20 centimeter. R2 is equal to minus 20 centimeter. Determine the focal length. R1 is equals to plus 20 centimeter. R2 equals to minus 20 centimeter. Determine the focal length when made from crown glass. Crown glass with N equals to 1.52 and flint glass with N equals to 1.66. You have to be alert. You have to be alert. This exam. I know the funniest thing, they're not far away. Those things you need to know plenty. Stop solving, everybody. Ancestors, thank you. How many of you know what they call a Gaussian surface? You know how to use Gaussian law properly. You understand? They tell you now, define a Gaussian surface, you can define it. What that a Gaussian surface is the surface that what? A Gaussian surface is a surface that encloses all what? All electric flux acting perpendicular to the surface from the inside. So, no. This is where we people. But note it down. That's what I'm mentioning it, so that you can go to your secret place and check it out. Now, how many of you can differentiate between antiferromagnetism, diamagnetism, paramagnetism, and ferromagnetism very well? Those things are very simple. Your para, it experiences weak repulsion to magnets. Your dia, they experience weak attraction. These things are not, like when you calm down, you find that they don't even go far. But when they ask you an exam, you see that the way they will ask it and not the way that will just state one difference between each of the following. You will not have anything to write. On something you used to hear every day, you don't have anything to write. What's up?
How many hours you want gather?
Just get in there. 5. No problem. Now, how many of you, at this point in time now, cannot still explain Rayleigh's genes defect in classical physics? Last 3 years, they asked Samo when they were talking about ultraviolet catastrophe. They asked about it briefly. This year, as of you, we have not still revised. Hydraulic press, hydraulic press, hydraulic press, hydraulic press. What are the systems we apply hydraulic press? Brake pad. Can you explain the mechanism of the working of the hydraulic press in the brake pad? You cannot. You cannot explain the working principle of the hydraulic press in an hydraulic lift. I see the exam you are going to write. It's common entrance, some of you are prepared for. You have to make sure that your mind is set, your spirit is awakened. Gone through well, in your dynamics, I just believe that banking is not a problem, right? Banking is no longer a problem. Conical oscillation is no longer a problem. It's alpha blessing. I want to believe no problem again. Wall of death. Because one of the free body diagrams of one of these things I mentioned is going to come out. Either wall of death, or you will see something from earthwood system, probably composite earthwood. Composite earthwood, or something will show up. You need to be active in the mind. So you prepare yourself for that. Yamune. Prepare yourself for that. Prepare yourself for that. How do you calculate absolute pressure? OBJ question. Hmm. It's minus now. What is it? That's that you'll be asking yourself in there now. Is it minus or plus? Something that we boldly wrote and explained. I even give you reasons how to remember when it's plus or minus. So now you say it's written. Minus. I be plus. Which one did you say? See, I've used time and give you guys a lot of aspects. I've opened your eyes to the things you need to do. From today like this, we are going to be continuing from elements of modern physics, which we have almost wrapped up. I repeat, do not forget your AC circuit. They not do what? They done it yesterday, the night. And the tickets now. That's where they are. All right. So we are going to be mentioning some questions. I will mention the questions. From those questions, I will be linking them up into things that you might need. Yes. That's one of the help I can do because we've run through this program. We've covered exactly 30 concepts completely from the module. Not in the inline module, from the recommended text. The question I want to ask now is this. Who can explain the implication of an isobaric system on the thermodynamic equation? I know you should define isobaric. What is it? Okay. That means work is equal to 0. So for isobaric. What about isochondric? The same thing. Same thing. In an isobaric system is a system where what is constant. Abi? Then isovolumic or isochoric is a system where what is constant. Now, in the expression, is there anything like change the pressure normally there? So what does it mean? It means that it does not have any effect. It does not have any effect on the work done. It doesn't at all. Listen, that's normal work. Normal work done in the gaseous system is measured as pressure times the change in volume. Yeah. Links with thermodynamic system. Yes.
So the formula that is going back to that was another constant molar pressure, which is the NCP. The NCP.
Okay. Look at this question. See this question now, for instance. Now see this thing. He said, I don't even need you to solve. Just tell me what you think that is appropriate for you to do. Hot combustion gases expand adiabatically. Hot combustion gases expand adiabatically through a rocket nozzle. Initial conditions are pressure which is equal to 8 megapascal, temperature 2200 Kelvin, exit pressure 100 kilopascal. Given that y is equal to 1.25, determine the exit temperature. Then determine the ratio of exit volume to chamber volume. Then C, determine the specific work extracted. You are confident you know this, what to do there, to play on low. You had my question. They give us two pressure, yes. So when they give you two pressure, now you know what to do and low. So my own question for you now is, what do you mean by exit temperature? And what's the meaning? Okay, what's the meaning of specific work extract? These things are things you know. They just mention it in another way and now you're looking. It's not why. You mean why like vertical component or something? No. This thing they're talking about the drag force in air and thrust in air. That's the thing that they're talking about there. When you talk about specific work. That's it. Because that's what we need to overcome before the other side of the rocket is turned down. It's a reverse physics question. A gas expands adiabatically according to PV raised to the power of specific heat ratio and is equal to capital letter C with y equals to 1.35. Determine an expression for the work done by integrating the put factor there. I know that was not an issue. Please, out of auto cycle and auto cycle and what do you call it? Carnot cycle. Go and learn the two very well. One will come out. I'm coming. Let me just do myself. flowing models. They will list the models. It's not for you to now tell them, in this model, this is the centripetal force. In this model, this is the centripetal force. In this model, this is the centripetal force. For example, what produces the centripetal force when a charge enters into a magnetic field? When a charge enters into a magnetic field and it starts moving, what induces its centripetal force? That's one example I'm talking about. Number two, when you are whirling your rope round in your hand, what produces the centripetal force? That is another one. Number three, what's it? Number three, when a car is making a turn, it's making a turn on the road, what produces the centripetal force? When the planets are moving around the sun, what produces the centripetal force? Mention 5 motions that are curvilinear with examples. Projectile motion is an example of a curvilinear motion. Good. Me, I'm expecting you to tell me hyperbolic motion, elliptical motion, parabolic motion. That's what you're supposed to be mentioning, circular motion. Open all those are curvilinear motions. Open circular motion is a curvilinear motion. Magnetic, for one of yes. For example, electron moving around moving in its orbit. What's producing its centripetal force? Which magnetic force? You're not speaking English. Food. Electrical field. Go and eat. Go and eat and come back. They are showing signs and symptoms of starvation. When you are rolling a rope, it is tension that serves as centripetal force. The tension in the rope will serve as centripetal force. Planets moving around the sun, gravitational field. But some of them are now going to write gravitational field and leave it like that. Gravitational field of who? Gravitational field of the sun. Because the larger one, hope you know gravitational, the sun have gravitational field. Because the law is the universal law. It works not only it works generally. Every universe is attracted to one another by a force. The reason why it looks like nothing is attracting the sun because the sun is huge compared to the planet orbiting around it. Not late, there's still very much time. What I'll just tell you is those aspects that I've highlighted, you can't do it well. Those parts I've highlighted. What force is responsible for the distributive flow of fluid as a result of viscosity in a tube? Thank you very much. Who said it? Thank you very much, Wisdom. Share. No, yes. And share force, another name for share force is the what? It's the tangential force. That is the force. That is why when a fluid is flowing in a tube, you find out that the places closer to this thing are usually behind. This is how the fluid used to be. This side they are usually moving fast, meaning that there's a kind of pull from the walls that are still creating a reluctance around the edge. Do you understand now? That's the case there. And they might give you the might. That one is they might do it to you. If they don't do it to you, say up to God already. There's something important that elasticity I'm remembering. Yes. Is there anything like a plastic point? Yes. In your Hooke's law graph. There's plastic point, I mean. And there's also yield point. What do you call your let me tell you something here. See. Yes, who's calling me there? Alpha. See, that's where I'm going to. And it is not plastic points. You are talking about the point where you are hearing it breaking. See, there is nothing like, based on JUPEP A-level exams, there's nothing like plastic points. What we have is plastic region. That's what we have. Oh. The line that is drawn straight down from your yield point down, everything from that point down to the right is called plastic region. From proportionality limit down to the left is elastic region. In between those two lines is called what? It's called what? No. It's called what? You say it's what? Eh? Elastic region is to the left. Region is to the right. That side is transitional region. Region of transition. You will see many things online. You will see many things. You will see plenty of things. We have seen, we have time. Now, when electrons or radiation knock off, I hear me? When electrons or radiations knock off electrons from their position in the KL series, what kind of S-ray is about to be produced? The name of that void is called the what? The name of the electron that has been struck off is called the what? It was here I drew it. The electron that the radiation pushed off was called the what? When we explain it in relation to Compton effect, let me remind you, don't worry. I don't know. My mom said I should not be reminding people anything. Anything that they have in their book, like you remind them that you are deceiving yourself. Now, why can you open the book? Hope you know how to derive Bose radius, Sha. That one is good on that end. Hope you guys know how to derive Bose radius. Hope you know how to link it with Mosellus law. State Mosellus law. That what? Is it frequency or square root of frequency, madam? So why did you say that one, what you said before? Look at this question. The shortest wavelength. Hello? The shortest wavelength. No. Let me not assume. Inshallah. The shortest wavelength and emitted from an X-ray depends primarily on hello. An electron and a proton are accelerated through the same potential difference. Which particle has the greater de Broglie wavelength? A. Electron. B. Proton. C. Equal. D. Depend on voltage. B. Electron. C. Equal. D. Depend on voltage. Why proton? No, your reason is correct. Your answer is wrong. Who has a lighter mass between electron and proton? A lighter mass between the two of them. Has a lighter mass than electron? Hello? Proton and electron, which one has a lighter mass? Electron mass is even negligible in the first place. It's too small. Like they even say that the atom, they don't consider its mass a part of the mass. What bears the mass of an atom is what? Proton and neutron only. So your reason was correct, but your answer. When your wavelength is the when your wavelength, sorry, when your path difference is a whole number of wavelengths, the waves formed are said to be what? Now, what is the formula that we use in determining and confirming that? The formula for path difference. Call it now. I don't hear you. Thank you very much. An electron through 80 kV strikes an X-ray target. The maximum photon energy is dash. An electron accelerated through 80 kV strikes an X-ray target. The maximum photon energy is dash. What's the answer? Strikes an X-ray target. You try, but let me give you the options. A, 80 eV. B, 80 kV. C, 8 MeV. D, 0.8 keV. Because I don't know. A, 80 eV. B, 80 keV. C, 80 MeV. D, 0.8 keV. Because wait. KV as in, because they don't keep that KEV, but yeah, correct. Hello. The wavelength of an electron increases when A, its momentum increases. B, its speed increases. C, its kinetic energy decreases. D, its mass increases. I don't hear you. Decreases. Increases. Sharp. How many of you still have that material? Don't worry. If you have that material printed at that time, go and answer these questions. That's my advice for your ultimate advice. All right. How many pi dimensionless terms are present in a variable in a 5-variable system that contains three fundamental dimensions? Thank you. Professor. She said 2. How is it 2? It's kind of advanced.
The number of the variables minus the number of the minus the number of the minus the number of the word. Wait.
If I polarize, you buy my head back.
Minus the number of
I'm giving you 2 minutes to look for a helper. I will help you in this situation. Once you fails it, you and her and soup. Fundamental dimensions. Huh?
minus m, you get your answer. What's m?
They want to just learn this like problem. And you're asking them, by this time, I know Dave and Dom. Something you Dave and Dom for like 5 minutes. Very soon now we'll start. We'll start the second session. I need us to finish this thing. Hello. A gas expands adiabatically. A gas expands adiabatically. All right. A gas expands adiabatically according to a gas expands adiabatically given specific heat ratio of 1.35. Given specific heat ratio of 1.35. the pressure decreases continuously from 3 MPa to 0.5 MPa. Determine megapascal. Huh? No, it is to 0.5 MPa. Determine, hey, those of you there, you took the know the other part. Determine the pressure decrease. Sorry, determine an expression for the work. Determine an expression for the work done. Then evaluate numerically. What's the answer? What's the answer? Mm-hmm. I don't hear you.
What when the mathematics system is equal to V1 minus V2 V2 over specific bit ratio minus 1.
Like the expression. Let's call it again. Call it again. Like call the expression again.
V1 minus V2 V2 over y gamma minus 1. Where gamma representing specific bit ratio.
You can do it like that. You can also do it like that. Eh? So, no.
Go and read.
Let us solve problem. Let us solve problem. Oh, yeah. Okay, I've not solved it. You have not solved it. It's no issue. There are many ways you can express it now. How many of you wrote that formula down? What's the question again? Do you know K is? In that expression, do you know K is? Eh? K is called adiabatic constant. Hello, those of you that pity you. K is called adiabatic constant, also known as process constant. Now, for a reversible adiabatic process, the pressure and the volume must satisfy that the PV raised to the power of specific heat gas ratio will be equal to constant. Which constant are we talking about? That particular adiabatic constant. So that means if they not give me P2, V2, and they give me that constant, I can say that that constant is equal to P1, V1. Raised to the power. You understand what I'm saying? Did you do that? The constant was written for you then. I know if it's constant. Check your question. I'm assuming that is the question I give people to do is read it out. That's not the question I was even expecting people to. That's not the one. And you people are suffering. I'm on my WhatsApp here. This other one is direct. This other one is the normal. Put your P1, V1, all those things inside now. That no issue. The C that you're seeing there is still your normal C constant. They give me every other thing. If you give me P1, they give me P2, P1, V1. So what's your problem? What do you want? Huh? They don't give you one, but they gave you C. And but they gave you C, which is still constant. Okay, imagine now that C that they gave you. You make that C. The constant is also constant. That one did not give you the value, but you can work it out. That's what I'm trying to tell you. Because we know that that C is also a PV raised to be equal to a PV raised to the power of. Now, P is equal to C over V raised to power of specific ratio. True or false? From there, do you agree? P is equal to C over V raised to power of specific ratio. That means I can now tell myself that what? That work is equal to, because if I want to convert that stuff there to work, it will be very easy. From pressure to work, what am I supposed to do? Pressure to work, I multiply by volume now. That's what I would just do. Multiply both sides by volume. After I multiply both sides by volume, what will be having left? That means work is equals to volume C dV. Abi? Integrate that V. Yes, you don't need to. Yes, the same thing. You see, no, you cannot integrate the V. Like we are not. What we are looking for is the V. Is that V? Integrate that V. Only give you. Yes, in respect to. Yes, that's it. So +1, then bring it down. You know that the V will deal with you now. V is the power of. That's something I mean, don't know. And so when you're integrating it, you have V -1 all over. No, sorry, +1 all over minus specific gate minus +1. That's what you're having now. In an adiabatic system, what's the condition? But it tends to be adiabatic. You know that, hello, those of you that are there, hope you are listening. Normally, you must have heard of P1, V1 equal to P2, V2 as a normal something, right? But you were saying that P1 V raised power of this is equal to a what? Constant, true of us. True of us. Good. Now, we will now know again that normal, this thing that is here, that is equal to constant, right? We know by ourselves that there is one thing they are calling work that is also equal to P change in V, right? Then is it unwise for somebody to not feel that, oh, I can take advantage of this thing if this one is dV and use it and derive an expression for the work? If you do that, what will you be having? We say we'll be having work equals to what? Please, work because of what? Work because of what?
What you change the way and it's constant. No, like since work equal to keep changing, there's work equal to change the way and it's constant over previous powers.
That one, you are stressing yourself like that. Yeah. How do you understand integrating like that? This is no longer clean. Start very simple with the constant. Let the constant be the one to bring in the work for you. Normal, it is C that is equal to what? P V raised to the power of this. True or false? To the extent that you might take it as your P1, V1. Ramu. So what are we saying? What are we saying now? This is a constant, Abi. Good. As this thing is a constant, we also know that work is also equal to what? P in V like this. True of us. We can now even tell ourselves that, okay, well, this thing is like this, so that you want to integrate it. Like this stuff here, you want to integrate it It's because I'm writing work like this. I could do the work as W small. You need to work. If I integrate, you give me the full work. I mean, you not get. Everything in physics derivation can be written in small form when you are talking about you took an infinitesimal quantity of it. If I take infinitesimal quantity of every other thing that work depends on, it will give me infinitesimal work. And if I start to integrate the parts to get the whole, all I need to do is just to change this dependent variable into capital. Into capital letter W. Can you hear me now? Sure. So we're saying that this thing can be written as W equals to P dV. You understand why I wrote it like dV like this, Abby? Okay. So now, how do we bring and change this P? Because how do we work at this? Because now what we just need now is this expression shows us that we have to work a way to find we can bring in V so that we can differentiate V. And that thing has been waiting for us here. It has been waiting here. So what are we going to be having here? Constant with constant over what? I mean, true of us. So we can substitute it inside where? We can put it inside this region, right? I mean, for me, instead of me writing like this, I can just write it as CV inverse like this. Do you get? So we just put it inside there like that. So we're having W equals to integral of what now? From where V is equals to qualifying now, V final. This guy will have business with this guy. So what do we do next? We can do what to this? Integrate it. I wrote dx, sorry. What will I have? See something like this, Abby? So from here, what do we have? W is equal to C, something like this. B minus this plus over y plus 1. From a point where we have VF to a point where we have VI. Can you solve from there? Can you solve from there? Or it's still not good yet? But, okay. From there, we now have this is equals to capital letter C, open bracket. So in this place now, let's do for VF. So what am I having? VF, later on we'll change it to V1, V2, all those things. Or let's even use it now. V equals to 2, Abby. V equals to 1. So I'll just call it V2 plus 1 all over minus y plus 1 minus v1 y plus 1 now I'm giving what? We can, the thing that we're going to eventually what we're going to use is going to have pressure. But I'll come back and recall something from there to bring back pressure. The many things we can come back and recall. Why do we serve? Okay, yeah. So there's this thing that we're writing as y, please. Let's write it well. I can write it like this. What do you now have? I can factorize these two out of there. If I factorize these two out of there, W is now equals to open bracket 1 minus this. Now, if they not give us all those P and all those things, we can end here. If they give us, we'll record that maybe we said C is equals to this. C is equal to this normally. I'll just come here and before I will make my assumption, because the same way C is equals to that, C is also equals to the second value on. That is P2, V2. So it depends on what you want to use inside there. So that means I can have W equals to P1, V1, 1 minus this to give us that's it. With this, you can solve that question. Where is the question? You gas expand adiabatically, Abi. Where this is this. The question even say we should derive the expression. So that's the derivation. Numerical evaluation. We need to get V2. Yeah, now, so V2 is this one now, yes. Here P1, V1, this. So which one are we looking for that did not give us? V2. V2. They gave us V1. 0.01. Let me call it. Initial volume. V1 is there. It's there. So just not have it in mind. So once you have done it, you can get this one can work or the other one works. If you are in the situation where they did not give you C, or they give you only V1, then there is no what they call it, P1. You see, it's only P1 and the other P2. This can still help you get your work done. If you want to get P2. Oh, yeah. Okay? All right. Hello. Who can define Poisson ratio? Poisson ratio. Hello. Hello. Is that people have not finished? Yeah? So people don't know Poisson ratio. Lateral deformation over longitudinal deformation. That's it. All right. Now listen up. Listen up. How many of you here don't know how to work with your coefficient of restitution? You don't know how to work with your coefficient of restitution. Q. Look at this question. How many of you know how to differentiate between your... How many drag force do we have? We have 2 drag force. What are they? How many kind of drag force do we have? What are they? You mentioned physical force inside here. Yeah, that's even true. Now, Dwayne Hunt's equation. Do you remember it? Hello? No. The Dwayne Hunt's equation, do you remember? Hello, you're doing Hunt's equation, do you remember? I take it as a yes. Let me tell it for you. Yeah? You're doing Hunt's equation is the value that gave you this. So many of them converted to it already. That's the Hunt's equation. I wrote this EV. That's your Hunt's equation. That's off, guy. The mic. Battery. Battery. The no, yes, man. Is it similar derivation now? Like they used to relate it to the Brooklyn and energy. Hello. All right. Now see something. Two coherent sound waves emit equal, it's not calculation. Two coherent sound waves emit equal amplitude at one point. Complete destructive interference occurs. This means A, no energy reached, which is that point. B, energy disappears permanently. C, energy is redistributed elsewhere. D, the energy cancels throughout space. What? Okay. Hey. Hello. No energy reaches that point. No energy reaches that point. Energy disappears permanently. Energy is redistributed elsewhere. The wave cancelled throughout space. What is it? The wave cancelled throughout space. The wave cannot cancel now. The wave cannot cancel. I'm sure. You get? The correct answer is that energy is redistributed somewhere else. They have redistributed the energy. Spaceship traveled past Earth at 0.95 columns. Spaceship, I said column, 0.95 c, the speed of light. Listen, observer on Earth and observer inside the spaceship measure the speed of light emitted from the spaceship. Which statement is correct? A. Earth measures less than c. B. The spaceship measures greater than c. Option C. Both measures exactly c. Option D. The measured speed depend on their direction. Right now they calculate this thing. They do. Everybody do by the spaceship is traveling east, man. Over observers on Earth and others inside the spaceship measure the speed of light emitted from the spaceship. Which statement is true? Is what they think is written the thing. The truth about the matter is, you guys have to be studying. Both will measure exactly c, because speed of light, we said, can, no matter the reference frame you study it, you are going to get the same results. That's why it is the limiting speed. You can't measure more than that, and you can't measure light to be moving smaller than that. A perfectly insulated cylinder. A perfectly insulated cylinder. A perfectly insulated cylinder contains a gas. The gas expands freely into a vacuum. Which statement is correct? A. Temperature must decrease. B. Internal energy must increase. C. No work is done during expansion. D. Pressure remains constant. What's the answer? And then pressure remains constant. That's option D. Like, is that what you are going for? Option D. Why? Makes sense, but the answer is not there. The answer is no work is done during the explosion. No work is done. The perfectly is like an executing system. Nothing will happen inside. Nothing. Hello, those of you in that side. A satellite moves in a perfectly circular orbit. Its engine suddenly stop. Assuming no atmospheric resistance, what will happen? Pardon me. Okay. Which question? Satellite. Hello. A satellite. A satellite moves in a perfectly circular orbit. Its engine suddenly stops, assuming no atmospheric resistance. What happens? A. It spirals towards the earth. It flies off tangentially. It comes in and out. No, he said it comes in the same circular orbit. It slows down immediately. What do you think is the answer? Yes. What's the answer? The answer is it flies off tangentially. That is B. Means that I dey scared for them. I dey fear for una sef. Just come on. Okay.
One way forward.
All right. How many of us have understood the concept of sound waves? How many of us have understood the concept of sound wave? Doppler's effect. Hello? Doppler's effect. Depends on the door, and you have not had Doppler's effect. You have been hearing about it, Abby, and you did not do anything about it. Now, I've taught it before. So, a 1 hour to 2 hours dive into sound wave, shook leg and come outside is what I want to do. Let's go. What is sound? Hello? What is sound? Sound is the auditory energy or sensation. Sound is the energy we hear. As light is the energy we see, sound is the energy we do what? Hear. Are we together here? Yes. So you must understand that when you hear the word wave, follow me. Wave, we understand what that one is. Wave is like the material medium. Wave is like the opportunity that helps in transmitting different kinds of energies. And sound is now one of the type of energy that wave can actually carry and transport. So you can boldly tell yourself that sound wave is a wave that contains, or you can use the word transmits, energy of auditory sensation. That means you can hear it. It's an energy you hear. Before you now even chook your head inside way too much, you have to ask some basic questions. Questions like, what are the properties of a wave? of a sound wave. What are the characteristics of sound wave? They will ask you well. There are three major characteristics of sound waves. Three major characteristics of sound waves. Three major ones. What are they? Pitch. The next one is what? I can't hear you. Quality, thank you. Intensity, thank you. Breathe now. Breathe in the name of Jesus. I've written it. Then quality, bro. This quality, they always call it timbre. You people that call it timber. As archaic as you are, you're still giving yourself some level of touch. Intensity is also called what? Loudness. Are we together here? Are we together here? Now, each of these characteristics of sound wave depends on something, and that thing is very important. What does pitch depend on? Frequency. What does intensity depend on? Threshold of hearing. What does timbre depend on? Overtone and harmonics. What does loudness who can tell me? Aside from threshold of hearing, what's the other thing that loudness depend on? Before you say a wave is loud, amplitude. These three things we just mentioned now, there's no how you're not going to write one of them in your exam. There's no how we'll be in theory that you will not, your brain will need to help you to reflexly send this message to your prefrontal cortex. It's not possible. It must. Now watch. Watch. When you have known this one, the next thing you want to know are the terminologies used in sound wave. Terminologies used in sound wave. Hello. Terminologies used in what? Sound wave. First terminology I want us to learn. They call it what? We call it supersonic sound or wave, supersonic wave. We also have subsonic. We have infrasonic. We have what again? Ultrasonic. You see these two that are down here, they relate to the frequency of sound. They relate to the what? Frequency of sound. What am I trying to say? Infrasonic are those that move with their wave that move with frequency less than frequency of what? Sound. There now, which is about 10 hertz. Ultrasonic, greater than, frequency is greater than the frequency of what? When you talk about subsonic and supersonic, I'm talking about the speed of sound. I'm talking about what? Speed of sound. These ones, they move why? How do they move? Subsonic, less than speed of sound. And this one, greater speed of sound. Now, let us now talk about sound intensity and sound intensity level. Sound intensity and sound intensity level. When we hear the word sound intensity, what comes to our mind? It's simply look at something. Look at something. Sound intensity is just the general power of the sound per unit area. I can make a sound here, create a sound here, and that sound will have a specific region of area it encloses. Outside of those regions, people outside of those regions will not be stimulated by the sound. They won't hear it. I get what I'm saying now. So that one is what we call sound intensity. When we say sound intensity level, we are trying to look at sound as having layers, where we can easily say that people in this layer are hearing by this amount more than the ones here. This ones here are hearing by this amount more than the ones here. All those kind of things. That's what we're just saying. So, sound intensity what do you mean? Thank you. The power of sound per area. So we're saying it is P all over what? A. Power by area. Which, if we expand it, what do we have? It will become P all over 4 pi R square. True or false? Why that what? That's the area of the what? That one is the area of the what? Yeah. It's the area of what? Hemisphere. That's for volume. It's for volume. 4/3 pi R cube. Do you understand now? Are you good? Happy now? Normal. Yes. Because we are living on the earth. The sound of anybody on this earth transmits. That's why if you watch any cartoon, you will never see anybody where the sound is not like this. Do you understand now? So the sound will take the shape of the place it is propagated upon. That's it. So it's usually spherical. So this is it. What unit do we give to this? When we have power over area, what unit? What's the normal unit of power? Is it not watts? So this is where we have our what? Unit is watts per meter square. I write down like normal human being big. And I cannot remove this thing from my ear. But on the other hand, we can now also tell ourselves about sound intensity level. What did I say? Sound intensity level. This one is denoted as I. Sound intensity is denoted as what? I. It's denoted as I. Are we together here? But sound intensity level is denoted as B. Sound intensity level. What does this one say? Right. Sound intensity level gives information. Sound intensity level gives information. Sound intensity level gives information about the audibility of sound. The audibility of sound at certain distance from a source. So I will draw something like this now. Watch me. People that are at this level are more proximal to the source of the sound there. True or false? So they will hear the sound louder than people that are farther away. True or false? That's sound intensity level. So you now want to calculate what is the loudness of the sound on this linear region, this particular line. People occupying this region here, how are they feeling the sound? We are going to be relating the sound intensity in such a way that it can do that. And most times, what helps us to get such linearized functions are logs. They are what? Log. So, what do we have? We have B equals to what? 10 log open bracket I naught over I. This is the formula, and this guy is measured in decibels. For short, dB. Measured in decibel. I told you already. If you feel you have a choice, no unit, no wahala. If you feel you don't have a choice, also no wahala. The Lord is your strength. Let's solve some questions on this. I naught, threshold intensity. You have truly not done this topic before. Sound. What is that? Hello. The I naught is the I naught is what? Is sound intensity, threshold of sound intensity. She asked. Threshold of sound intensity. This one. It's supposed to be in this thing, in the denominator. I naught is threshold of sound intensity. And that's a constant 1 times 10 raised to the power of 10. So sometimes I can just call it 10 raised to the power of 10. What's the unit? Watts, meter. All right, let's pick this question now. And again, we know that the speed of sound in air is what? Approximately what? 343 Abi. And it increases when you get to more denser media. We will soon show that. 1.0 times 10 to the power of 10. Put the units there. Watts per meter square. Now look at this question now. A loudspeaker radiates sound uniformly with an acoustic power of 0.20 watts. 0.20 watts. I didn't hear you. I said a loudspeaker radiates sound uniformly with an acoustic power of P equals to 0.20 watts. So I'm having P equals to 0.20 watts. A. Determine the sound intensity at a distance of 8 meters. Sound intensity at a distance of what? 10 meters. Sound intensity I at a distance of 10 meters. Distance of 10 meters. I told us our sound intensity is what shape? Is circular. No, the sound intensity, like spherical, yes. It's covering a spherical area now, right? Very good. So therefore, what are we going to consider to be our area? What are we considering to be our area? They gave us a value already. The value they gave to us was what? 10. Abi? So what do you think should be our area? I'll tell you why. Read the question very well. It's clearly looking at you, Jay. It's clear. You don't just have to cram. The question was saying a loudspeaker radiates sound uniformly with acoustic power. The sound intensity at a distance of 8 meters. Look at it. At a distance of what? 8 meters. Check. Is it 10 meters? Sorry, 8 meters. 8 meters. At a distance of 8 meters. So what's going to be your sound, your radius? If you want to calculate it upon a smooth surface, what will be your radius? No. What do you say? Listen up. There are two ways. Listen up. You know I told you that we have sound testing and sound testing level. If you are dealing with that sound intensity, most at times, when the sound is not crossing kilometers, you will know that this thing is not going to be presented like a sphere. It's just like probably a smaller area now. So it's going to be more of 2D than 3D. Do you get what I'm saying? So in this case, we are going to be using what? This as the radius. Meaning that the person, look at the meaning. It means that if this person standing here and he propagated the sound and they want to look for how somebody in 8 meter distance will feel it, you agree with that this sound is actually something like this, of which you can complete it to form a full cycle to the back of the person. So what do you call this distance from where the sound was to this level they wanted? What will you call that distance? If it was a full cycle, is that not radius? So that's what we're trying to say. So automatically, if for this case, we are not going to be using 4 pi r. We'll be using how many pi r? The normal circumference of the cycle will be 2 pi r. So what are we having? P is equal to what now? P is equal to what now? Sorry, I is equal to what? P over 2 pi r. This D is our R. They still don't get it. Yes? Yes. Now, good question. Oh, sorry. Pi r squared. Thank you. Pi r squared. So, the individual there that asked D is diameter now. It's true. It appears as diameter in your eye. But if you come and if you look at it practically, if I make a noise from here, that noise transmits spherically around me. So I become the central focus for the propagation of that sound. So any distance from me to forward me or beside me is a radius. Do you understand what I'm saying now? Any of such distance is considered a radius. So we are using that as radius. So I is now equals to what now? Power what? 0.20 divided by 3.142 times what? 8 squared. What does that give you? What does that give you? .94 watts per meter square. Okay. Having done that now, how do we get, if they told us to get our intensity level, what are we going to do? What's the formula for intensity level? B equals to 10 log. Do you see that now? Come in. Next question says, a sound intensity. A sound has an intensity level of 82 decibels. A sound has an intensity level of 82 decibels. So I'm having what here? 82 decibels, right? So we're having B equals to 82. Right? We are looking for the intensity. We know that the threshold intensity is equal to what? 10 raised power of 10, Abby. So how can we get this? We just apply the formula. B is equal to what? 10 log I over what? I naught. So how can we do this? Divide both sides first by what? By 10. So what are we having here? 82 over 10 equals to what? Log I over what? I naught. So what do we have here? 8.2 equals to what? log I over 10 raised power of what? 10. You know, when you write it like this, it means that there's base 10 here. Hope you know. So let's open this thing. 8.2 equals to log 10I. Then we have minus log 10, 10. Hope you guys understood what I did there mathematically. Do you understand? So we are having 8.2 equals to log 10I minus, listen up, 10, 10 is here. You know it's 10, 10 that is here. 10 comes here, having 10 log 10, 10. 8.2 equals to log I 10 minus 10. True or false? Hello, true or false? This one can now go to this place. We're having what? 18.2 equals to log 10I. I think we're almost there. Final step. We can take this in and bring this out to remove the log. So I'm having what? Let me rewrite it like this. That is log 10I is equals to 18.2. I carry this one out and bring this one. So 10 raised power of 18.2 is equals to I. That's what it is. That's what it is. The help me press it in calculator. Let's see what we have. 1.58 times 10 raised power of what? Times 10 raised power of what? Are you sure what you are pressing? Okay. Yes. Okay. So we're having I equals to, call it again. Units. So that's that for that. That's that for that. Next question. Next question. They said the sound intensity is 5.0 times 10 to the power minus 6. The sound intensity is what? Yes? The value is now. Okay, I thought you asked me from the previous one. I just started reading it. The sound intensity is 5. Is someone calling me from there? 5.0 times 10 to the power minus 6. 5.0 times 10 to the power minus 6. So we're going to use it and solve. Are we together here? So what are we having? That's intensity equals what? 5.0. What's watt per square? Determine its sound intensity level. That means we're looking for what? We're looking for B. B is unknown. So what do we now have? We are having B equals to what? 10 log I over I naught. So what else do we do from here? Divide both sides by 10. Okay, this is what we're looking for. So no need of stressing. So B is equal to what? 10 log 5.0 divided by 10 to the power of what? 10. Log open brackets. We're having 5.0 times 10 to the power minus 6 divided by 10 to the power of 10. All raised power of 10. Calculator. Yeah. Punch inside first. 5.0 times times 10 raised to the power of minus 6 divided by 10 raised to the power of 10. How? Yeah. You can put it now, you know. It's possible now. It's possible. So what's the final answer there? Have you done the log value? B is now equals to what? 53 decibels. Now, please, when you're writing your decibel units, it's written in small letter D, capital letter B. Small letter D, capital letter what? B. My next. Determine the sound intensity level at. Determine the sound intensity level at. At 5 meters. This is 5 meters. So direct. The machine produces this distance at this. Okay, let's use this one. A listener is 30 meters. A listener is 30 meters from a loudspeaker producing 0.90 watts. The listener walks until the sound level drops by. What were you doing when I started? A listener is 30 meters from a loudspeaker producing 0.90 watts. The listener walks until the sound level drops for 8 decibels. Determine the new distance. Let's go. You guys attempt that. Look at it, attempt that. 2 minutes. Yeah, I said just have 2 minutes. So attempt. Give what? Sorry for you. A listener is 30 meters from a loudspeaker. Anybody? Yes, problem. A listener is 30 meters from a loudspeaker, producing 0.90 watts. The listener walks until the sound level drops by 8 decibels. Determine the new distance. Okay. Nobody? Okay. All right. So, no attempts. No attempts. Okay. So the question says, a listener is 30 meters from a loudspeaker producing 0.90 watts sound. The listener walks until the sound level drops by 8. Determine the new distance. Now, this procedure requires a bit of derivation. Can okay. I want to quickly use it as a bravo. You come back. I want to please. I want to come back.
Don't let me and people.
No, I'll take this time. Please just signal me when it's time. Oh yeah. So on this now, we are looking at how drops, how a drop in sound intensity level can result in a corresponding drop in sound intensity. So we will start from here. We will further record that B is equal to what? 10 log open brackets I over I naught. So that drop now, that means we are going to have two sound intensities. I said two sound intensity levels now. Because I said laser works until the sound level drop by 8. So we are going to be experiencing situations where we're having B1, because it's the drop in sound intensity levels that will give you a sound intensity. B1 and B2. Where if this is the B1, this will be intensity 1. And then if we have the B2, this will be intensity 2. Do you get what I'm saying? So, to make this more possible, we can't solve it. We have to open the two fractions to make them more linear. So I'll be having from this one here, I'm having B1 equals to what? 10 open brackets. This is log I minus log I naught. Which is the same thing as BI equals to what? 10 log I1 minus 10 log I naught. Right? So we can keep this now. So let's go for the next one. B2 equals to what? 10 log I2 over what? B2 equals to what? I naught, sorry. 10 log I what now? I2, no need of the brackets. I naught. So yes. What can we do from here? We want to bring this one here. Let's just bring this one under. See what this one just did? This is the B1 equals to 10 log I1 minus 10 log I naught. You can see how this one will cancel out. Abi? By subtracting. Not division, subtracting. Like elimination. Those ones have gone out. So let's add what we have here. So I'm having B2 minus B1. B1 as well. Anyone now, eventually. It depends on what we take each parameter to become. It's now equal to what? We're having 10 log. Ten log what? What do we do to this one? This is minus I2 over what? 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 I'll bring it out now. So from here now, what do we have? Even as I can't see anything, they're not benefiting. B2 minus B1 equals to 10 log what? So from there, you can divide both sides by 10. So this is how we calculate it. Subtract the two intensity level. Sometimes they give you that value direct. Like that one where they said it is 8. They've given you the subtraction already direct. Then here we're having what? 10 cancel 10 abi? Log I2 I1. Right? This thing has the year 10 on top here. So it means that I can express this thing as 10 raised to the power of B2 minus B1 all over 10 to be equal to what? Over I1. So this is the way you compare it. Where this is already the subtraction already. So that's how we do the derivation. So now, in this place, on this formula, they've given us the drops, 8 dB. Can you see that drop is in dB? So that's how you know that this whole place here is 8. So we're left with what? 10 raised to the power of 8 all over 10 equals to I2 over what? I1. Did they give us the I2 and the I1, all those things? But they made us understand that I2 is equal to, when you punch all this on the calculator, what will it give you? Help me check. Press the calculator, what will it give us? Are you sure? Very, very, very sure. What is it? What? 0.1 0.1585. Abi? It's like they gave us one of the intensities. A listener is 30 meters from the loudest speaker. This one, 4 pi. And this one said we will not need to open the area. We know that I is inversely proportional to R squared. So I, based on the normal formula, I is inversely proportional to what? R squared. So what do? I know that I1 R1 squared should be equal to what? I2 R2 squared. Right? That's what I'm doing. So from there, what do we now get? Maybe said they give us the first. That means I'm having but we can have is that working to this thing? We have now is initial position. It's the same person that worked. So it's coming from an initial time frame now. So what's it? So I'm having I1. What's that I1? I1 is 1. I1 is 1. Let's express I1 in one side so that we know what we're doing. So I1 over I2 equals to R2 square over R1 square. Abi? This is 1. Then this one now is the one that is, where is it? Where is it? Where is it? We've gotten this one already. See it. Look at what I did. Relating it. So I will say, all this one here, carry the square root to this side. That's square root 1 over I2. This one is 1 over, this one is I2 over 1. So we are saying 1 over 0.1585 is equal to, so they gave us one of the R's. Which one of them? Remember it's our I2 that is down. Which of them did they give us? I1. So that's 30 watts. So I'm having from, that's under here, 30 meters. Then my R1 square. Yeah, from here, there's no square again. From here, you can get it. Square this one for me. What does all this one here give you? So our final answer is R1 equals to what? R2 how? Okay, so our R2 is what we're looking for back. So our R2 is equal to what now? 47. 30 plus 2.5. 47. We've carried all the square here and square roots. 70 watts. Fast. I want to do something. 75.354 meters. So that's it. You can go through it, master it. I'm coming. So. Hello? Okay. So good day, everyone. Let's proceed. So, I think we're solving a question. We were done with it. Okay. Right, let's solve 2 to 3 more questions on this and we will move to the next thing. So now we have the sound intensity of a sound intensity of a sound has an intensity of the sound has an intensity of 1.0 times 10 raised to the power of minus 6. So we're having sound intensity 1.0 times 10 raised to the power of minus 6 watts per meter. Find its intensity level. So the intensity level of this sound intensity is B. So what do we have now? B is equals to what? 10 log I over I naught. B is now equals to 10 log, open bracket, I is what? And our I naught is what? 10 raised power. Is that what I used earlier on? No. Please, it's 10 raised power of 12. Correct it. Did we use, how many questions did we use and do it? No. Not possible. I will write it twice. Check. Confirm. Where? This is one question we visited. That's this. We will not use intensity like twice, 3 times. Check. It's up to 3 questions that we used. How many questions did we do? Two questions did not have it. This one we did that was not, did not have it. Regardless, please, it is 12. Regardless, it's 10 raised to the power of 12. I beg. Note it down, no. Note it down. Okay, so what else? So we have B equals what? 10 log. Open bracket what? I think this one now will give us, it's easier to divide now. 10 raised to the power of minus 6 minus 12. Is that not supposed to give us? You've done it straight. What's the answer? Minus 180 dB. Okay. You check the way you're pressing this thing. Check. Sorry, minus 12. That's plus. See, my brain is already off. Press it. Let's see. Approximately 60, Abby. All right, let's go. Next one. A sound has an intensity level of what? Solution. Sound has an intensity level of what? 50 decibel, have you? B is 50 decibels. Calculate its intensity, I. So what does this one give us? It's helping me check the numerics. Because I'm kind of only flat my brain. A equals what? 10 log I over I naught. Remember, I naught is minus 12. So B is equals to 10 log. What's our I? Now I can enter B now. 50 over 10 raised power minus 12. So we have what? Divide both sides by 10, divide both sides by 10. They are doing everything together. So I is now equals to what? It should be giving us times 10 power minus 7. Okay. So what do we have? That's it now, yes. I know. Next one. Before we go into something. The next one says the sound intensity. The sound intensity is call it to me, please. Okay. No. Sound intensity is 1.0 times 10 power minus 5. Find the sound level. So in this case, they give us the sound intensity. They want us to get the sound level. So what would that be? Ten log I over I naught. This is 70. So our B is 70. All right. So, I think it's quite enough that we just, I think we solved enough. Let us go to the next part, like next theoretical thing inside here, which is relationship between sound, speed, and other stuff. So they can ask you what are the factors that affect speed of sound. When you know the factors that affect speed of sound, then you'll not be able to start dealing with the calculations that surround them. Factors affecting speed of sound. The speed of sound, are we together now? Speed of sound depends on how easily the medium can be compressed. Because what happens before you say that speed is easily transferred in the medium, or in a place that maybe speed is fast somewhere, is based on how easy it is to compress the medium. And that plays a vital role, like compressibility. Because speed travel making use of refractions, like repeated refractions and compressions, right? So, in essence, we're going to say elasticity, because that's elasticity. Ability to compress medium. Elastic properties, such as medium, should be able to play a role here. And then another thing again that will affect speed of sound is density of the density of the environment is too high. It's going to affect. Don't pass. You know what does happen now? I thought that someone was carrying me already. Oh. Where am I? So the speed of sound V is equal to the square root of what? Modulus. But if the medium is spread, the more elastic the medium is, the shorter, the more easier the sound will travel. So I know that one is going to be up. Modulus. Then do we get that now? Modulus and density. Modulus and density. Those are the things there that contribute to all these things. So V is now equal to what? Okay, that's it. So let's talk some questions on that. Hello. The mic battery is dead. So, it doesn't connect. So, So another factor again that sound depends on is temperature. You know that the more temperature increases, the more the speed of sound increases. In fact, From a normal standard temperature of about 331, sound increases for every 1 degree rise in temperature by about 0.16. Do you get what I just said? Do you understand what I just said? I said that for every 1 degree rise in temperature from a standard temperature value of 331, which is about room temperature, temperature will be rising by 0.6. That is the speed I mean, the speed of sound will be rising by 0.6. You get what I'm saying? So look at this. But just to draft out a relationship, temperature varies, speed of sound varies directly with the square root of temperature. I get you now? And I said, for every 1 degree rise in temperature, comma, for every 1 degree rise in temperature, comma, the velocity increases okay. What is it? So what are we having now? So we're saying that okay. So that's it. That's it. Let's get into questions. Let's go into questions. Start the calculation questions. So is there no battery again? I think no battery.
You think?
This one.
Continue lecture. We'll fix this. Continue lecture. Fix this one.
So all right, so all right. The bulk modulus of a liquid is 2.4. Take.
Just in the system. Say something.
Hello.
That's why battery is draining. We did this to 3. I will increase volume here.
Okay. Hello.
Is it better?
Yeah, it's good.
We just volume to 1 up to 2.
Okay.
That's why the battery is draining. Stop.
That's off.
I'll just use this one. Is it better?
Hello.
Is it better?
Yeah.
If you think I just let me know.
Okay. Recording. All right, so the bulk modulus of a liquid is 2.4 times 10 raised to the power of 9. And its density is 1,200 kilogram per meter cube. Calculate the speed of sound. Calculate the speed of sound in the liquid. Okay, calculate the speed of sound in the liquid. So what do we remember here? Modulus of our density. Let me press it, please. Everything 1 for 1 for. The solid has the modulus. The solid has the Young modulus of 1.6 times 10 to the power of 11. Eh? 3.6 of it. 1.6 times 10 to the power of 11 in modulus. Oh, yeah. What's the value? Yeah. It remains just 30 hours to beat this person record. Rest. The camera is watching. So, find the speed. I could. So this is it. A solid has a Young modulus of 1.6 times 10 raised to the power of 11 Pascal, and density of 6400. So as usual, it is the modulus over the square of the modulus over the density, be it Young modulus, be it anything. That's just it. So here now, V is equals to so we have 500. Oh. Okay. Speed number 3, the speed of sound in air. Speed of sound in air at 0. So now 0 is 331 meters per second. So at this point now, we are saying the speed of sound is at 0 degrees Celsius, and this is what the value is now. So we have V equals to 331 plus 0.6 theta. So the theta now is estimate the speed at 30 degrees Celsius. So I'm putting 30 here. So in your exam, in case you see such, don't forget. So we're having 18. So V is equal to 30. So what are we having? I don't know. Next question, what is it? So they said a gas has no, it's direct. I'm sorry. The gas has the speed of sound at 340. The gas has the speed of sound of 340 meters per second. The gas has the speed of sound at 340 meters per second. So we're having a gas at 3. Yes. It's made the speed at 432. So we're going to look for the speed. I'm looking for speed at 432. So you can recall that velocity is proportional to t. So v all over t1 equals to v2 square root t2. Are we there? So v1, what's our v1 there, please? 340. What was the temperature for 340? 300, have you? It's now equals to v2. V2, what's v2? You know, that's what I'm looking for. V2 over square root 432. Okay, the final value, Abby. Okay, so well, answer will become 408. Abby? That's per second. The speed of sound is 5,100 meters per second. The speed of sound is what? 5,000. Huh? The density is 7.8. Speed of sound. Yeah. But this is the same thing as over density now. That one was very funny. 2 points. That's it, though. Before the most screenshots. Okay. I guess the gas. Which one is direct? Alright. Yeah, no. What's that inside? What's the inside? You're not be comfortable. That's your can't hold it. You can't be comfortable with it. Just continue. Call. So we're having now. Yes. So bulk modulus. Okay.
Speed of sound. Speed of sound is 1,000 seconds.
So speed of sound.
1,500 seconds. Time density.
So having v squared equals to b all over rho. Then we're looking for rho. Rho is equals to b over v squared. One point eight divided by
1,500 squared.
1,500 squared. This is nice. This one. I thought I put square already. It's okay, that's it. Okay. Let's go. So here we are having v squared is going to be equal to. So we are looking for density, right? So we are not having density is equals to b over v squared. So yes. So we're having this is equals to 1 point. Okay. Divided by
1,500 squared.
so what do you now have?
800 over meter cube.
Liter.
Meter cube.
Next one. Let's take some higher questions. Something more serious. Okay, that's all. That's all. We'll go to the next aspect now. Okay. So we're able to touch sound intensity level. We're able to touch all those things. So now I'm going to sound in strings and pipes. The next one we're going to sound in strings and pipes. Hmm? Okay. I'm taking 5 minutes. That's all, man. A pipe. Okay, so what we're going to now is pipes. Alright. Let me get water. Stretch strings. Oh. A stretch string has length equals to 0.80. Okay. Stretch string has length equals to this. So this is what it looks like. This is a string. Let's imagine the string is fixed at the supports. Alright. Okay. Okay. Alright. So these are the length of L. That's the length of L. And we refer to this as the fundamental frequency. Because that's the first harmonic. Fundamental frequency is raised as the first harmonic. So just to quickly describe, these regions are the nodes, which are the regions of minimum displacement. Yes. Have you done before? Done before. So we have lambda. F is equal to V over 12. This is fundamental frequency. F is equal to V over 12.
So just continue. Don't
Okay. So imagine. So then we have this is the fourth harmonic. One only just third harmonic, second over two. This is first over two. So it's third, second over three. So we must see it. You can see. So all right. This is how it is with pipes. Okay. Yeah. Okay. Okay. Hmm? I don't know. Is it? Which one? This one. Vanilla, open pipes and similar. And the same is string. Just small change. You don't need to make the approach is different. I'm not like handling it once. Listen. Eh? It's already past 1 hour here. Um, MC is one. But I know. I did see 1 hour here. But let him confirm. Confirm first. Hello. I'm back. Okay. So for pipes, we have two kind of pipes. We have open and closed pipe. So an open pipe it's quite as simple as you are saying, and you can find out. At both sides. That's just like this one. Open at both sides. Just like this. Air can come in from here, can come in from here. But the closed pipe is one that just opened at one side and closed at the other side. So sometimes it might not be that it is closed, it might be with a water column filled to a particular level. All right. So we'll be looking at let me back that charger. We're doing open pipes. So when it comes to open pipes, it's quite almost exactly the same with strings. The mass distribution is the same. Yes, for the length for the length relationship between wavelengths. Yes. I'm not giving you what. I'm going to give you the diagrams. I'm using it. As we are drawing it, I'll give you diagrams, the formula, the way we did it. When I drew each of them, and I give the diagrams. So this for the first, or we call the fundamental level. Then we assume that this other one here for the next one. We draw this. Okay, so that's it. So each of these things represents a circle. So this is like 1 circle, like 2 circles, 3 circles. So we still have that normal distribution you have in your pipes. So the first one there is this is your length. Then we'll be having your 1/2, and that the lambda is then equal to 2L. So we recall that frequency is equal to V over lambda. So in this first stuff here, we have it F equals to V over 2L. So that's on that or that. So that's on that. So for this one, we're having L to be equal to lambda. And that implies that on our formula where we say F is equal to C over lambda, we'll be having C over L. That's the type shape. So the same thing applies on this. We have our length, as usual. The relationship of our arbitrary L constant n to length of this one is going to be n. That will be 1, 2, 1, 2, 3. And again, if I will move on, there's a way, short way you can count it. Utilizing the nodes, the attributes. So here, these regions of intersects are the nodes, right? So we have those of the nodes. One node. We have this representing 2 nodes. How many nodes do we have in this one? 3 nodes. So what will it become? We're going to be having L equals to. So when you cross multiply, you have 2L equals to 3 lambda. Therefore, lambda is equal to 2L over. So if you want to represent this in our formula method, you just recall that F is equal to C over L. And in this case, no. Sorry, C over lambda. So in this case, no. F is equal to C, 3C over 2L. So let's bring it out. The relationship of continuity. So the fundamental on our open pipe is literally F equals to V over 2L. After V over 2L, we have the next one. So let me just remove the F. So the next one was where we had 2C over 2L. The next one is where we have 3C over 2L. So recall that fundamental frequency was fundamental frequency was V over L. These are still V's. V's are C's. It depends on what to, let's use V. Speed. So V all over 2L. So if you notice, you can extract V equal to from everything. So that gives me F naught from this, and for this here that goes down, I have 2 F naught. This that goes down, I have 3 F naught. This is my harmonic. This is fundamental notes, fundamental frequency called first harmonic. This is the second harmonic, which is the first overtone. This is the third harmonic, which is the second overtone. Yeah, but that's where the difference is with closed pipes. So in our closed pipes, I'm going to put closed pipes on this. In our closed pipe, we have something like this. Let me imagine I brought that to this over here. So closed pipes. So the wave travels in, comes in there, comes out. That's one of the diagrams. In another diagram, we have something like this. So in this place here, I promise. So on this one here, we have this. So on this one here. Now the difference between what we're doing in open pipes, how are we doing in closed pipe, is that in this one, you only have odd number harmonic. And the arbitrary number on top only odd. Yes. The wavelength. You count it, like we count it with the nodes or antinode. Like this place now. You know that a wavelength is a full cycle. So in this place like this is, if I continue from here, it comes down and comes there. It's a full cycle. I can get two crests.
Just one node and two antinodes.
Yes, one node.
Two antinodes.
It does not have to be like that. The easiest way to count a full is to see the full cycle.
Okay.
You understand? See something. This height. Can you see?
Yes.
You know, normally this is not the diagram will be. The correct way the diagram would be something like. So we want to see a full cycle, something like this. That if you bend this one like this, you see it close one full cycle. So this one here, we can never get a full cycle on, like a full direct cycle from the nodes. You understand?
Yes.
And there's nothing like a node that they have inside pipes. People just imagine it. Yes, it's not like you know that they have, because the diminishing point of that wave can be at the quarter of your wave. It might not exactly be at the half. And there's no way to measure it. So here now, we use over 4. So on this one, I'm going to be having what? This is the first fundamental. I'll be having my L to be equal to lambda over 4. The next one is going to be odd number. L will be equal to 3 lambda over 4. You get that now? Usually what I'm counting now, I'm my internal system. I'm counting this 1, 2, 3. So now it's just 1. 1, 2, 3. 1, 2, 3, 4. You get? So this is like 1, 2, 3. So I'm going to be like, on this after the third one, I know I'm going to the which one?
5 over
4. So the rule is we don't have any odd number something. Good. We don't have any odd number something. So the lambda is equal to 4 here. The lambda is equal to 4L over 3. The lambda here is equal to what? 4L over 5. So following this same something now, I have F is equal to what? F is equal to C over, let's call it V all over lambda. That's the general numerator somewhere. So automatically, this is going to be F equals to 4L. On this one, I'm going to have F is equal to 3B over 4. And this one, I'm having F equals to 5B over 4. Now, notice something. Notice something. If I bring out that same arrangement now of my stuff, I'm having what? I'm going to be having fundamental frequency F naught was giving me V all over 4L, the first harmonic. Right? Yes. So if I look at the distribution, I found that this is the first harmonic here. We can call it F naught. I can extract my first harmonic from here as well. I'm having 3 times of that first harmonic. I can also have 5 times of the first harmonic. So this is first harmonic. This is third harmonic. But this is where people get people confused, even jam. As this is third harmonic, it is the second, it is the first overtone. It is the first overtone. Regardless, overtone is still counting normally. This one is the fifth harmonic, is the second overtone. You get your fundamental note and not overtone because they are still fundamental. So with this, we have come to the end of the draft of pipe and strings. So what we want to go into is a more important thing, which is the Doppler's effect. Then I will start, having we're done, we'll start solving questions on every of these aspects. You get? So what's Doppler? What's Doppler? What's Doppler's effect? Now, Doppler's effect studies speed of observers and source. It studies how an observer senses sound relative to his motion, relative to his state of motion. You understand? And it's normal. If we find ourselves moving towards a source of sound, right, we get to start hearing the sound clearer. If we're moving away, the sound fades, right? So if the source and the observers are both approaching themselves, you even start hearing the intensity of the sound more, right? And if they are recessing themselves and if they are moving further away from themselves, the sound begins to even fade out easily, right? So what we are doing is this. We are going to be creating conditions with signs, conventions that satisfy different Doppler's situations or states. So I'll be bringing out those conditions one after the other. We'll be drafting equations that satisfy all of those conditions. So here now, before we move on, let's just define Doppler's effect. Doppler's effect describes the observation of sound frequency by an observer relative to a source. Relative to a source. Do you understand what I'm saying? Okay, so let's pick the first situation we want to pick. Before we start picking the situation, let's get something straight about the speed of sound. Normally, velocity is equal to what? F what? Right? Okay. So, know this. You know this one. So the thing I want to do now is, let's imagine wavelength is constant. Because wavelength is actually constant. Right? Let's imagine wavelength is constant. So we want to work with these two. Right? So if I'm working with these two, what will I be having? V is proportional to what? F. So that means V is equal to KF. Here we will now see K is equal to V all over what? F. So therefore, V1 over F1 is equal to V2 over what? F2. So the question we'll now ask ourselves is this. The question we'll now ask ourselves is this. We're not going to be using 1 and 2. Let's be using observer and source. So let's call the 1 observers and call the 2 source. So that means I'm having what now? I'm having V observer over frequency of observer should be equal to source. Okay, very good. Frequency of source. Now, the real deal about Doppler is we want observation of frequency to be the major point of concern because that's one that will be dependent. The source frequency can be controlled by the source, but the observer cannot control the audibility of the source. It can only move away from it or choose to move towards it. You get?
Yes.
So therefore, I'm going to be working with relative speeds. You get? Basically, but let's first make our observer subject of formula. What should I be getting? Subject of FO.
V naught times Vs.
V naught. Let's write Fs first. Fs V naught over Vs. You get it now? So now that we have this, let's put this thing relative to the normal speed because this speed now, this thing here is the velocity of the observer. You get? That's the velocity of the observer relative to the speed of sound. Do you get? Relative to the speed of sound. So we are going to actually use that plus or minus. We're going to be using all those plus or minus. So it's better we represent it as F naught equals to Fs V plus or minus V naught over V plus or minus Vs. Do you understand what I did here?
Yes.
So that's it. This is our Doppler's equation. So we're now going to be creating the circumstance to study the Doppler's effect. Just now. Okay. Yes. So, Doppler's situation 1. So, our first situation will be a moving observer, the observer moving towards a stationary source. Do you understand? Yes. Yes, situation 1. Observer moving towards a stationary source. So we have observer moving towards a stationary Stationary source. Observer moving towards the stationary source. So what happens then? Observer moving towards the stationary source. What's going to happen on that? What do you think will happen there? So this is it. Imagine this is the source of the sound is not moving, it's stationary. The police siren. Just imagine. Them and just siren. Let's manage that siren. So when we say stationary, that means its velocity is equal to what? 0. That's the source. Right? So this is the observer. And he is moving towards the source with a speed v o. Right? This thing actually, do you understand this thing before? You don't. They ask about it in Japan, so better learn it as well. When I check the past question, it comes out. People just run away from it because they don't know it. So they just believe it. Meanwhile, it's bonus, physics 02. It's bonus. Whenever they ask, you know that they put lights and sound. Many people prefer to do that and do lights. And at least sound for owners. So meanwhile, it's actually simple. You see for yourself. So the observer is moving towards. So it's not like greater than line mass. It's going to be more easier for me to explain to you what it really is. If the observer is going towards the source, right? What do you expect to be happening to the hearing? This sound is going to become louder in the observer ear, right? So look at this fraction. You know, Fs is a constant. The frequency of the sound coming from the sound is constant. We can't change that. But this is where we can play with. So this is where you demonstrate your exceptional technique to be able to know what fraction is correct to use. Now, the observer, based on that condition, the observer is going to be hearing the sound louder. So obviously, I need to position this fraction in such a way that I will be supporting a resultant big answer, not disobeying the fact that the observer is what? That is, source is stationary. So source stationary means that Vs is going to be equal to what? 0. So I'll be left to totally V of that. So the numerator, do you think the numerator should be bigger a value or smaller a value for me to end up with an observer hearing more? So what do you think? That means I have to use plus instead of minus. That's how it works out through. Like that's what you're going to be doing for all this circumstance. Once you can play that game right, then good to go. See now. So in this case now, what do we see by doing? That is F is now equals to F is open bracket what now? Divided by what? That's it. So Doppler's intuition 2. What's Doppler's situation 2? 8 minutes. What's Doppler's situation 2? Yeah. Sorry. Yeah. You can use anyone next. There are about 6 situations you can draw out. So this one now we can say, we can say the source is moving towards the stationary observer. And we know that that will still increase the observer's loud sensation. If I'm going 2 ways, I will hear it loud. If I'm approaching the police siren, it will be loud in my ear. If I'm stationary and the police siren is approaching me, it will still be getting louder. So this one now is source moving towards station observer. So what does that give us? Yes, because an observer is stationary now. So you understand, it's just the real analysis. Finish. So this one is stationary. Our police car. Our police car has bro is moving towards us, man. So what do you think we should do with that fraction now? So you know that the up now, observer is stationary. So there's nothing we can do to the up because it's only V that is there like this. So the down, then we need to put the minus so that it can be small. But when it's small, it will give us a big resultant value.
Yes.
You get it now? So by using V, say V is remaining divided by
Yes.
Doppler situation 3. Doppler 3. The third one. This one now we're looking at. We've done observer moving to stationary source. We have done stationary source moving to. You see,
Source is moving to
a stationary observer. So the next one we can do now is a source moving to an observer moving away. Because we will still do a source moving to an observer moving towards. We'll do for a source. Let me just do like this. Source and observer moving towards themselves. That one now must do things to both the up and the down function. Because this is why this one was a bit straight, is because you know now 0 has taken the middle. But now the two will be open each other. So we do something to both the up velocity and the down velocity. Then when they're moving away from themselves, right? We'll do something too. Then when they are moving in the same direction, just that maybe the observer is moving faster or in the same direction. As that of closing gaps. Understand? So that's the situation. Not crazy. Let's go. So what do you say? No, I cannot waste it. See the time. It means me. I will die for years now. I will put extra. I think like 20 minutes, 20 hours. Never even drink one finish the talk. This guy is funny. What's that? Oh. So yeah, what do you now have? Observer. Approaching themselves. So we need to give, because approaching themselves is the situation or sharing word, is the position that will give the highest level of audibility. So we have to set it such a way that the denominator supports that loudness. So that simply means I need to do something that makes my numerator big and do something that makes my numerator small. And that's saying V plus V not have it. V
Yes.
sure. So tell me, is this naturally hard? Don't promote the drum. That's why I just wonder why they skip it in the exam. Why? Why? Dope. So, that's why I stand up again. You are right. So, what do we have? What is it? What is it? Yes. That situation is easy. 0, 0, they will just be having. It just, that means there will be no change. There will be no change in the way they be hearing it. The audibility is the same. Automatically, 0 now. Here will be 0, here will be 0. Then V will cancel V eventually. So you believe you only F not because yes. Not like no, see, their frequency will now be the same, yes. They'll be receiving as the same frequency. The frequency will not be the frequency your source was using to hear it will be what you continue using to hear it. What the observer was using to hear it will be the same thing we using to hear it. It's not saying that hearing the same frequency. Obviously, the source, the sound is near him now. But both of them will not experience any change. Okay. Observer, because we're doing the observer and source. What do we call it again? When they're separating away. Observer and source separate as recession. And I've written the recession of observer and source. So this one now is also moving away. Let's run and move it towards. What's the question? This one, you think about it. Let me see what you say. Yeah, you think about it. They're separating from themselves. This one, this one here. This one was smaller. So this one now, what do you expect? Smaller. They will not be there anywhere. So as the numerator is small, the denominator should not be still small like it. Yes. Yes, man. If you make the numerator big, you're giving advantage now. Even when he goes to decide it, you're giving him advantage. Yes. So anytime you put plus, you have given numerator advantage. Even if you come and you've reduced the numerator and still use the small freight you have to reduce the numerator again during rehearsal. What's the situation? So, what is the next circumstance? Where is the where is their what? They are moving away from themselves. Let me just this. Both stationary. That one not really serious. You don't same direction as the one we've not done. But that's the one I've never done. They're moving in the same direction. But that one is not empirically obtainable. Because the question is, they're moving in the same direction. And that depends on how they are moving. Yes, these are the, you know when you start, I told you this for. That's the four empirically obtainable ones. Very well done, sir. That's fine. What is there? After this one, I just had to touch it. We saw many questions outside with. Then and I'll look at No. My playing syllabus. I'll be playing on live stream. Thank you so much. Thank you. Let's go. So, I think we're done with you. Well, let's create questions. Let me bring out the class question sharp. The former pipe. Example. Where I'm going to it. Yeah, it's plastic. Did you see my textbook? I posted it on the group now. Not today. Since, I think last week. Before this event started, I completed it and packaged it. Alchemy of Physics. Alchemy of Physics. I did it for you now. These Korean people be like, I did, but not for percent. It's for essence. No. Like, I have printed it down now. I have my copies. I started printing right now. You know, that's where I am. I don't like it. I like black. Guy, I don't need my phone. Yeah, so That's it. Yeah. We'll be solving questions now. We'll be solving questions now. I'm done with this. And an open pipe, an open organ pipe is 1.2 meter long. The speed of sound is 1.344 meters per second. And generator is the question. I will do this thing. An organ pipe is 1.2 meter long. The speed of sound is 344. The fundamental frequency. Sandwiches. Yeah. John, these ones. We have eaten it. We have sold everything. Yeah, that's from here. Give me the laptop. Which one is that? Read it. Which goes on?
Speak. Find the product about this.
Aye. It just mean like 60 hours. Just be like say my brain don't exchange. As you look in this place, this pole here is doing me like the mirror here. See na mirror there. I'm not dey comfortable. It's feeling like upstairs. Feeling like upstairs. Just stop feeling. You just appear. The wavelength of each image. That sounds like refund. The wavelength of each image. Sounds like refund. I'm getting the wavelength back now. The wavelength of it's, I see. So let us get lambda. Value is 2. And then they said you should just give this expression. I'm not able to solve this. Let's get the answers. What's the length? 1.2. So this one is 2.4. This one is unless not just possible. Small steady. Every next hour counts. I'm done with this one. Next. If I closed at one was end, not forget it. Let me know of these books. Chill. What about it for me? Or enough. Don't do this thing. Don't worry. Thank you.
It's a question like this one now. It's a question involving open pipe or closed pipe. This particular question.
This one.
Yes, sir.
For close pipe over 4.
Closed pipe.
Let me just go explain the calculator. What is fundamental frequency? 349 and 3.1. These are the train. The train was area 25 kilometers per second. 25 meters per second. We'll find the observed frequency. For observed frequency, so the observed frequency is equals to frequency. Okay. Frequency. Police frequency. Those gaps. Police center. This one. The police center. Citizen. Zero, ¿cómo se llama? The police prepare the place. No, 200 years. Como was it? We don't know what's going on. This was most maximum. This is. Yep. Oh,
Because not because
because the person.
of some
Because
because of some
the one is not the siren, the car.
yes.
The source moves out. I don't know if you want to start. This is a police siren. Is that what it's now? The police siren. The siren, the police siren station.
And the source of justice is right.
Yes. Yes.
That's why it's not.
That's this one.
Yes. That's why I think.
That's what it is.
Now, the real was which is that was
This is it's only not the game. It's supposed to be related speed. That's why I do this. It's so smooth. This is trying to prevent on the next one. So this is this one. You guys are amazing. This is sorry, come on. I see the class is running. Okay. And the whistle is moving 800 and then with the speed of 30 with the frequency ahead by the driver. So therefore, I'm going to be having frequency of the driver that's using by the driver will be able to frequency of the source. And then going towards another, so there will be average V plus V or V minus V and V naught equals to VO. So whereas V is 800, I mean 800 bracket V 0. Speed of Yeah. I think it was train B. That's true. No, 3, 11, 3, 1, 3, 1, 1. No, it's any operator. Yes, 3, 1, 1. Look, I will. Yeah. You said 3 plus 1. It should be plus 3. This is just the thing. This is just standard.
That is.
So there's no glass there. It's looking like there's a glass there. So you calculate what's the value?
98.0.
986.04 times. And that plus. So So moving now from here, moving now from here to this is circuit from the previous. So the circuit is one which they can exist in one component, three components, two components simultaneously. This is okay. So So the let's do this. What? I'm done with the question. The capacitor of the microfarad is connected to a 16 amp. You can just the result that you is going to break down. Top and then we have some support. It's 200. Yes. Result was in series as story Kansas. Chicago 55 minutes. Yes. There's a 50 groups. Everything. Without it. It's 130. Correct. No. So it seems like this. So we have the circuit like this has resistance, importance, articles. So supply the frequency. So put the section. So I keep it simple. Once again, we have counts of all of them. So starting from that, it has a real positive. What we need from this, which should be strictly into yes. Put a little bit more close. Simplify them. So the next x is equals to 1 over 2 pi xt 2 times 5 1 over 2 is equal to 1 as frequency. Frequency is 60 times capacitance over 80 times 10 to the power minus 6. Then we have impedance. Value equals where we start from was which is 5 squared plus x7. What is value of x7?
X7 is 75.40.
Value is
40.
so 4.86. The answer is correct. Is to do just 5 amps and 12.6 volts. Yes. This one is balance. Let's go for it.